story of nuclear energy is one of humanity's greatest triumphs, a saga of unlocking the immense power hidden within the atom's core. In the 20th century, this breakthrough reshaped the world, lighting up cities, revolutionizing medicine, and even propelling ships through Arctic ice. Today, as we stand in the third decade of the 21st century, nuclear energy is experiencing a renaissance, a resurgence driven by an insatiable global demand for power and an urgent need to combat climate change. This is not just a tale of technology, it's a narrative of human ambition, resilience, and the relentless pursuit of a cleaner, brighter future. Welcome to the new era of the peaceful atom. Why is nuclear energy back in the spotlight? The world is hungrier for electricity than ever before. Electric vehicles hum through our streets. Data centers powering artificial intelligence hum around the clock, and burgeoning populations in developing nations are plugging into modern life. This surge in demand collides with a pressing reality. Our planet cannot sustain the environmental toll of fossil fuels. Coal and oil plants belch carbon dioxide, warming the globe and choking the air, while renewable sources like wind and solar, though valuable, falter under the weight of weather dependency and land use. Nuclear energy, by contrast, stands as a titan of efficiency. A single reactor can power hundreds of thousands of homes for decades, emitting negligible carbon, comparable to the cleanest wind farms. It's a reliable, high-output solution that doesn't flinch when the wind stops blowing or the sun sets. But the peaceful atom's reach extends far beyond power plants. In hospitals, nuclear technology is a lifeline, with radioactive isotopes targeting cancer cells with surgical precision, sparing healthy tissue. In the vastness of space, nuclear engines promise to carry humanity to Mars and beyond, outpacing the chemical rockets of yesterday. On Earth's frozen frontiers, Russia's nuclear-powered icebreakers carve paths through Arctic seas, delivering supplies and enabling scientific exploration where no other vessels could tread. These are not mere technical feats. They are testaments to the atom's transformative potential. The journey to this moment has been anything but smooth. In the mid-20th century, nuclear energy was a beacon of hope. Scientists, having unlocked the atom's secrets, dreamed of a world powered by near-limitless energy. The Soviet Union led the charge, launching the world's first nuclear power plant in Obninsk, a small town that proved atoms could illuminate homes rather than destroy them. This sparked a global race, with nations from France to the United States building reactors at a dizzying pace. By the late 20th century, nuclear plants were generating enough electricity to rival entire coal industries, with France emerging as a powerhouse, supplying most of its electricity through reactors and even exporting surplus energy. Yet the path darkened. Catastrophic accidents, 3 Mile Island in the United States and Chernobyl in the Soviet Union, cast long shadows, fueling public fear and skepticism. These disasters, coupled with falling oil prices and bureaucratic hurdles, stalled the industry's momentum. New reactors stopped rising, expertise began to fade, and nuclear energy seemed relegated to the sidelines. But the tide has turned. Rising energy demands, coupled with the existential threat of climate change, have reignited interest. Innovators like Elon Musk champion nuclear as a cornerstone of sustainable progress, while new technologies promise to make reactors safer and more efficient than ever. Enter thorium, a lesser-known element poised to redefine nuclear energy. Unlike uranium, thorium is more abundant, produces less waste, and is inherently safer, shutting down gracefully in emergencies rather than spiraling out of control. Meanwhile, small modular reactors, compact, flexible, and cost-effective, are opening doors to nuclear power in regions once deemed impractical. These advancements signal a shift. Nuclear energy is no longer the risky giant of old, but a refined tool for a sustainable future. This text will guide you through the epic arc of nuclear energy. We'll explore its origins, from the skepticism of scientific giants to the triumphs of the first reactors. We'll dissect the crises that nearly derailed it and the innovations, like thorium and modular designs, that are fueling its revival. Beyond power plants, we'll uncover how nuclear technology heals, explores, and navigates, and we'll peer into the future, where fusion reactors, mimicking the sun's own power, could unlock boundless energy. This is the story of the peaceful atom, a force that has shaped our past and will define our tomorrow. Let's step back in time to unravel the epic saga of nuclear energy, a journey from the wild skepticism of brilliant minds to a dazzling era when the atom powered the dreams of nations. This is the story of how humanity tamed the most formidable force in nature, turning it from a scientific curiosity into a cornerstone of modern civilization. It's a tale of doubt, discovery, and triumph, with a cast of visionary scientists and a backdrop of global ambition. Welcome to the history of the peaceful atom, where the impossible became reality. Picture the early decades of the 20th century. The world of science was buzzing with excitement over the atom, but also steeped in doubt. Giants like Ernest Rutherford, the man who first mapped the atom's structure, Berzelius dismissed the idea of harnessing its energy as the stuff of mad dreams. Albert Einstein, no less, echoed this sentiment, declaring that atoms would never yield power on demand. It was as if they'd need to split themselves willingly. Their skepticism wasn't born of ignorance. It was grounded in the sheer complexity of the challenge. Splitting an atom to release energy was one thing, but controlling a chain reaction, where one split nucleus triggers others in a cascading dance of energy, was a puzzle that seemed unsolvable. Imagine trying to choreograph a billion tiny explosions, each one unpredictable, each one smaller than a speck of dust. If a single neutron veered off course, the whole process could fizzle out. To the greatest minds of the era, from Enrico Fermi to Igor Kurchatov, this felt like chasing a mirage. Yet the mirage began to take shape. In the late 1930s, a French scientist, Frédéric Joliot-Curie, made a breakthrough that shook the scientific world. His experiments showed that a chain reaction wasn't just possible, it could sustain itself. One neutron splitting an atom could release more neutrons, which could split more atoms, and so on in a controlled frenzy. This discovery flipped the script. Suddenly, the atom wasn't just a theoretical playground, it was a potential powerhouse. Robert Oppenheimer, who initially scoffed at the idea, calling early experiments nonsense, soon joined Einstein in urging the American government to fund nuclear research. Their plea sparked the Manhattan Project, a colossal effort born in the shadow of war. While its immediate goal was military, the seeds of peaceful nuclear energy were planted, waiting for the right moment to bloom. That moment came in the early 1940s, when Enrico Fermi achieved the unthinkable. In a makeshift lab beneath the bleachers of a Chicago stadium, he built the world's first nuclear reactor, dubbed the Chicago Pile. This wasn't a sleek machine, but a crude stack of uranium and graphite, carefully arranged to coax a chain reaction into life. When it worked, it was a quiet revolution. No explosions, just a steady hum of energy. Fermi's success proved that the atom could be tamed, not just for destruction, but for creation. It was a beacon of hope, signaling that nuclear power could light homes, fuel industries, and reshape the future. Scientists began to dream big. Glenn Seaborg, a leading figure in nuclear research, envisioned nuclear-powered rockets to the moon, artificial hearts driven by tiny reactors, even swimming pools warmed by plutonium. These ideas, published in a landmark book called The Atomic Age, captured the world's imagination, setting the stage for what was to come. Fast forward to the mid-20th century, and the peaceful atom took its first real step into the world. In a small Soviet town called Obninsk, a team led by Igor Kurchatov did something no one had done before. They built and launched the world's first nuclear power plant connected to a public energy grid. This wasn't a lab experiment, it was a working station delivering electricity to homes and businesses. The Obninsk plant was modest, capable of powering only a small community, but its impact was monumental. It showed the world that the atom could serve humanity, not just threaten it. The scars of Hiroshima and Nagasaki were still fresh, but Obninsk offered a different vision, atoms lighting up the night, not erasing it. Kurchatov and his team worked in uncharted territory with no blueprints or precedents, solving problems through sheer ingenuity. Their success was a testament to human grit and a spark that ignited a global movement. The world took notice. In the mid-1950s, Britain followed suit, firing up its own nuclear plant at Calder Hall. A year later, the United States joined the club with a shipping port reactor, and soon after, France brought its Marcoule plant online. These were the early notes of a symphony that would crescendo over the next few decades. By the late 20th century, nuclear power was no longer a novelty. It was a global force. The turning point came in the early 1970s, when a geopolitical storm shook the world's energy markets. A conflict in the Middle East sent oil prices soaring, leaving nations scrambling for alternatives. Nuclear power, immune to the whims of oil markets, became the answer. Countries poured resources into building reactors, and the growth was staggering. In just a few decades, nuclear plants went from powering small towns to rivaling entire coal industries, supplying electricity to millions. No country embraced this more than France. In the wake of the oil crisis, French leaders launched an ambitious plan named after a visionary politician, Pierre Mesmer. The goal? Energy independence through nuclear power. France didn't just build reactors, it built an empire of them. By the late 20th century, most of the country's electricity came from nuclear plants, a feat unmatched anywhere else. France wasn't just keeping its own lights on, it was selling surplus power to its neighbors like a baker with too many loaves. This was the golden age of nuclear energy, a time when the atom seemed poised to dominate the world's energy future. Scientists, engineers, and policymakers alike saw it as the key to a new era of prosperity, where clean, reliable power would fuel progress for generations. But this golden age wasn't just about electricity, it was about dreaming bigger. The same scientists who built reactors imagined nuclear-powered ships crossing oceans, planes soaring without fossil fuels, and even cities on the moon powered by compact reactors. These dreams, while sometimes fanciful, drove innovation. The Soviet Union, for instance, began experimenting with nuclear-powered icebreakers, vessels that could carve through Arctic ice to open new trade routes and support exploration. The United States explored nuclear propulsion for spacecraft, laying the groundwork for future missions to distant planets. The peaceful atom wasn't just lighting homes, it was pushing the boundaries of what humanity could achieve. This era of optimism and ambition set the stage for nuclear energy's rise, but it wasn't without challenges. The road ahead would test the industry's resilience as accidents, economics, and public perception loomed on the horizon. Yet for a shining moment, the atom was a symbol of progress, a testament to what humans could do when they dared to dream big. From the skepticism of the early 20th century to the triumphs of Obninsk and beyond, the peaceful atom proved that even the smallest particles could spark a revolution. The golden age of nuclear energy was a time of boundless optimism, when the atom seemed destined to power the world into a bright, limitless future. Reactors sprang up across the globe, lighting cities and fueling dreams of a new era. But like any epic tale, the story took a darker turn. By the late 20th century, the nuclear dream faltered, caught in a storm of economic shifts, catastrophic accidents, and a public that grew wary of the atom's power. This is the story of nuclear energy's crisis and stagnation, a chapter of setbacks that nearly dimmed its light, but also set the stage for its remarkable comeback. Let's set the scene. The world of the late 20th century was changing fast. The oil crisis of the early 1970s, when conflict in the Middle East sent fuel prices soaring, had made nuclear power the darling of energy planners. It was clean, reliable, and free from the whims of oil markets. Nations like France leaned hard into nuclear, building reactors that supplied most of their electricity and even exported surplus power to neighbors. But as the 1970s gave way to the 1980s, the winds shifted. The oil crisis eased and prices for fossil fuels plummeted. Suddenly, coal and oil plants looked like cheaper bets again. Building a nuclear power plant, on the other hand, was no small feat. These were massive projects requiring years of planning, armies of engineers, and vast sums of money. The price tag kept climbing, not just because of the tech, but because of something else. Red tape. Governments, spooked by the growing complexity of nuclear plants, began piling on regulations. Safety standards tightened, and rightfully so. Nobody wanted a reactor cutting corners. But every new rule meant more paperwork, more inspections, and more costs. In many countries, the energy sector was being privatized, shifting from state control to profit-driven companies. For these businesses, nuclear plants started looking like risky investments. Why sink a fortune into a reactor that might take a decade to build when a gas plant could be up and running in half the time for a fraction of the cost? The math wasn't adding up, and the momentum of the nuclear boom began to slow. Then came the accidents that shook the world. In the late 1970s, a nuclear plant in the United States, called 3 Mile Island, suffered a partial meltdown. A mix of equipment failure and human error let the reactor's core overheat, releasing a small amount of radiation. Nobody died, and the environmental impact was minimal, but the incident hit like a thunderbolt. Headlines screamed danger, and the public's trust in nuclear power took a hit. People began to wonder, was this technology as safe as promised? The answer was still forming when, less than a decade later, a far greater disaster struck. In the mid-1980s, in a place called Chernobyl, a Soviet nuclear plant became the site of the worst nuclear accident in history. A flawed reactor design, coupled with human mistakes during a test, led to an explosion that ripped the plant apart. Radioactive particles spewed into the air, spreading across borders and leaving a trail of devastation. Workers and first responders lost their lives, entire communities were uprooted, and the land itself bore scars that linger to this day. Chernobyl wasn't just a tragedy, it was a turning point. The world watched in horror, and nuclear energy, once a symbol of progress, became synonymous with peril. The image of a glowing, unstoppable reactor haunted the public imagination, fueled by newsreels and grim stories. These accidents weren't the sole reason for nuclear's decline, but they were the spark that lit a fire of doubt. Popular culture piled on, turning nuclear power into a villain. In a famous animated show about a family in a town called Springfield, the local nuclear plant was run by a greedy, cartoonish tycoon who embodied everything people feared: negligence, profit over safety, and a whiff of danger. This wasn't just entertainment, it reflected a growing sentiment. Nuclear plants, once hailed as engineering marvels, were now seen as ticking time bombs, too risky and too expensive to justify. The fallout was stark. In the United States, new nuclear plants stopped being built altogether. Projects that were already underway were scrapped, and existing reactors aged without replacements. Across the world, the pace of nuclear expansion slowed to a crawl. Some countries like Germany began talking about phasing out nuclear power entirely, betting on wind and solar instead. The expertise that had fueled the golden age started to slip away. Young engineers and scientists, seeing little future in nuclear, turned to other fields: computers, biotech, or renewables. The knowledge built over decades, from the gritty work of pioneers like Igor Kurchatov to the grand visions of Glenn Seaborg, began to gather dust like ancient scrolls left on a shelf. But this wasn't the end of the story. Even as nuclear energy faded, the world was changing in ways that would pull it back into the spotlight. By the early 21st century, the cracks in the fossil fuel system were impossible to ignore. Cities grew, industries expanded, and new technologies like electric cars and smart devices demanded more electricity than ever. At the same time, the planet was sending warning signals: rising temperatures, melting ice, and raging storms. Fossil fuels weren't just dirty, they were unsustainable. Renewables like solar and wind were gaining ground, but they couldn't provide the steady, round-the-clock power needed to keep the world running. Nuclear energy, despite its tarnished reputation, started to look like an answer again. A new generation of voices began to champion the atom. Innovators like Elon Musk, never shy about shaking things up, called nuclear power a critical piece of the puzzle for a sustainable future. Unlike coal plants that choke the air or gas plants tied to volatile markets, nuclear offered a stable, low-carbon solution. And it wasn't just talk. New technologies were emerging to address old fears. Reactors were being designed to be safer, shutting down automatically in emergencies. New fuels like thorium promised less waste and fewer risks. Even the economics were shifting as long-term investments in clean energy started to make sense again. This turning point wasn't just about need, it was about rediscovery. Countries like France, which had never wavered in their commitment to nuclear, stood as proof of what was possible. While others scaled back, France kept most of its electricity coming from reactors, exporting power and keeping emissions low. Their success was a reminder: the peaceful atom hadn't failed, it had been sidelined by fear and short-term thinking. As the world faced a new century with new challenges, the stage was set for nuclear energy to rise again, not as a relic of the past, but as a cornerstone of the future. The story of nuclear energy is a tale of harnessing the atom's might, but not all atoms are created equal. For decades, uranium has been the star of the nuclear stage, powering reactors that light up cities and drive progress. But there's a new contender in town: thorium, a lesser-known element that's sparking excitement as a safer, cleaner, and more abundant alternative. As the world rediscovers nuclear power, the race is on to decide which fuel will shape the future. This is the showdown between uranium and thorium, a clash of technologies that could redefine how we power our planet. Buckle up, because the peaceful atom is about to get a serious upgrade. Let's start with the basics. Uranium has been the backbone of nuclear energy since the dawn of the atomic age. It's the fuel that powered the first reactors, from the makeshift Chicago pile to the sprawling plants of today. But uranium is a bit like a high-maintenance rock star. It's powerful, sure, but it comes with baggage, complex processing, safety risks, and a legacy of waste that lingers for generations. Thorium, on the other hand, is like the quiet genius in the wings, ready to step into the spotlight. Found in greater abundance across the Earth's crust, thorium promises a smoother, safer, and more sustainable path to nuclear power. To understand why, let's break down the differences, from the ground they're mined from to the energy they unleash. First up, getting the fuel. Digging uranium out of the Earth is no picnic. It's often found in low concentrations, meaning you need to move mountains of rock to get a usable amount. Worse, uranium mining comes with a nasty sidekick: a radioactive gas called radon that can cause serious health problems. Miners need sophisticated ventilation systems just to stay safe, driving up costs and complexity. Thorium, by contrast, is a breeze to extract. It's far more plentiful, found in much higher concentrations in places like India, Australia, and Norway. Better yet, thorium doesn't kick up toxic gases during mining. It's like the element is ready to cooperate, eager to get to work without the drama. Once you've got the raw material, the next step is turning it into fuel. Here, uranium's high-maintenance nature really shows. Natural uranium is mostly made up of an isotope that's useless for chain reactions, with only a tiny fraction capable of sustaining the process. To make it work, uranium has to go through a costly and intricate process called enrichment, boosting the proportion of the reactive isotope. This isn't just expensive, it's a geopolitical headache. Enriched uranium can be used for more than just power plants. It's also the stuff of nuclear weapons, so every step is watched like a hawk by international regulators. Thorium sidesteps this mess entirely. The most common form of thorium is ready to go straight from the ground, requiring minimal processing. No enrichment, no fuss, and no risk of fueling anything more dangerous than a power plant. Now let's talk about the heart of the matter. What happens inside the reactor? Uranium reactors rely on a self-sustaining chain reaction, where splitting atoms release neutrons that split more atoms, creating a cascade of energy. It's a brilliant setup, but it's also a bit like riding a wild horse. If something goes wrong, say a cooling system fails or controls malfunction, the reaction can keep galloping, potentially leading to disasters like the one in Chernobyl. Stopping a uranium reactor in an emergency is like trying to rein in that horse mid-charge. Thorium reactors, by contrast, are more like a well-trained steed. They don't sustain a chain reaction on their own. They need an external source of neutrons, like a small amount of uranium or another trigger, to keep going. If trouble strikes, you just cut off that source, and the reaction stops dead in its tracks. No meltdown, no chaos, just a graceful shutdown. There's a special kind of thorium reactor that takes safety to another level, the liquid fuel reactor. Instead of solid fuel rods, these use thorium dissolved in a molten salt. If something goes haywire, the liquid can be drained into a safe container, halting the reaction instantly. It's like flipping an off switch for the entire system. This design makes catastrophic accidents almost impossible, addressing the fears that have haunted nuclear power since its early days. Imagine a reactor that doesn't just tolerate mistakes, but shrugs them off with ease. That's the promise of thorium. Efficiency is where thorium really shines. A small amount of thorium can produce a staggering amount of energy, enough to rival hundreds of times its weight in uranium or millions of times that in coal. This isn't just about raw power, it's about getting more bang for your buck. Thorium's efficiency means you need less fuel to achieve the same output, stretching resources further and reducing the strain on mining operations. And then there's the question of waste. Uranium reactors leave behind radioactive byproducts that stay hazardous for thousands of years, requiring elaborate storage solutions deep underground. Thorium reactors, by contrast, produce a fraction of the waste, and what they do leave behind is far less troublesome, losing its radioactivity much faster. This makes disposal simpler, cheaper, and far kinder to the planet. There's one more ace up thorium's sleeve. It's a dead end for weapons. Uranium, when enriched, can be diverted to build bombs, which is why nuclear programs in some countries raise global eyebrows. Thorium, however, transforms into a form of uranium that's nearly useless for weapons due to its intense radiation, making it a nightmare to handle for anything but power generation. This makes thorium a diplomatic darling, ideal for nations looking to harness nuclear energy without sparking international tensions. Imagine building power plants in regions once considered too risky, knowing the fuel won't end up in a warhead. That's a game changer for global energy security. The world is starting to take notice. In the early 21st century, China made headlines by launching the first commercial thorium reactor, a liquid salt design that's as cutting edge as it sounds. This wasn't a lab experiment, but a working plan, proving thorium's potential on a grand scale. India, sitting on some of the world's largest thorium deposits, is pouring resources into its own thorium-based program, aiming to power its growing economy with this abundant fuel. Other nations like Norway and Canada are exploring thorium reactors, with research programs pushing the boundaries of what's possible. These efforts are still in their early stages, but they signal a shift, a recognition that thorium could be the key to a safer, more sustainable nuclear future. Uranium isn't going anywhere just yet. It's still the workhorse of the nuclear world, powering most of today's reactors with proven reliability. But its limitations, high costs, safety risks, and waste headaches, are hard to ignore. Thorium, with its abundance, simplicity, and safety, feels like the next chapter. It's not perfect. Setting up thorium reactors requires solving technical challenges like finding the right materials to handle molten salts or fine-tuning the neutron sources. But the potential is undeniable. As the world grapples with rising energy demands and a warming planet, thorium offers a path forward, one where the peaceful atom doesn't just power our homes, but does so with less risk, less waste, and a lot more promise. The peaceful atom is rising again, like a phoenix from the ashes of doubt and decline. After decades of stagnation, nuclear energy is reclaiming its place as a cornerstone of the world's quest for clean, reliable power. Across the globe, nations are forging their own paths, some doubling down on proven technologies, others betting on bold new ideas. From sprawling power plants in Asia to compact reactors in the West, the nuclear renaissance is a tapestry of ambition, innovation, and strategy. This is the story of how the world is rediscovering the atom's potential, with each country writing its own chapter in this new era of nuclear energy. Let's start with China, a titan in the nuclear revival. Not long ago, China's energy landscape leaned heavily on coal, choking cities with smog and fueling a ravenous appetite for power. But in recent decades, the nation has pivoted, embracing nuclear energy with unmatched zeal. Picture a country building reactors faster than most can build highways. China has transformed from a newcomer to a global leader, with dozens of plants now humming across its vast terrain. What sets China apart is its willingness to push boundaries. In the early 21st century, it launched the world's first commercial thorium reactor, a liquid salt design that's safer and cleaner than traditional models. This wasn't just a technical feat, it was a statement of intent. China is betting big on thorium alongside conventional reactors to fuel its booming economy while slashing carbon emissions. The nation's leaders see nuclear as a path to energy independence, a way to power megacities and high-tech industries without leaning on foreign oil or gas. With plans to expand further in the coming decades, China is setting the pace for the global nuclear renaissance. Meanwhile, Russia is playing a different game, one rooted in experience and global reach. Russia's nuclear story is steeped in history, from the pioneering days of the Obninsk plant to today's sprawling reactor complexes. The nation's approach is like a master craftsman refining a time-tested design. At a factory in a city called Volgodonsk, engineers are churning out reactor components at a pace that surpasses even the Soviet era's peak. These aren't just for domestic use. Russia is exporting nuclear know-how to the world. Countries like Turkey, Bangladesh, Egypt, and Indonesia are building their first nuclear plants with Russian expertise, from blueprints to training. Take Turkey, for instance, where a massive plant on the Mediterranean coast is set to light up homes in the near future. Russia's strategy is conservative yet ambitious. Stick with proven uranium-based reactors while expanding its influence as a nuclear superpower. This blend of reliability and global outreach keeps Russia at the forefront of the atomic revival. Across the ocean, the United States is taking a different tack, focusing on innovation over scale. After decades of standing still, new reactors were barely built since the late 20th century. The US is now betting on a new breed of nuclear technology, small modular reactors. These aren't the hulking giants of old. They're compact, flexible, and designed to fit where big plants can't. Imagine a reactor small enough to power a remote town or a military base, or a Morsianchi Wapri, built in a factory and shipped to site like a high-tech Lego set. Companies like NuScale are leading the charge, crafting reactors that are cheaper to build and easier to maintain. The beauty of these designs is their versatility. They can be deployed in rural areas, industrial hubs, or even disaster zones, providing steady power without the massive upfront costs of traditional plants. The US, sees these reactors as a way to revive its nuclear industry, blending cutting-edge tech with practical economics. While progress is slower than in China or Russia, the first of these modular plants is expected to come online in the coming years, signaling a cautious but promising return to the atomic fold. Not every country is on board, though. Germany, for instance, has chosen a different path, one that's raised eyebrows across the globe. In the early 21st century, Germany made a bold decision to shut down all its nuclear plants, betting instead on wind, solar, and other renewables. The move was driven by public fear, rooted in memories of past nuclear accidents, and a political push for a greener image. But the reality has been messier. Without nuclear's steady output, Germany has leaned on coal and imported power, often from nuclear-heavy neighbors like France, to keep the lights on. Critics, including outspoken figures like Elon Musk, have called this a misstep, arguing that abandoning nuclear in a world desperate for clean energy is like throwing away a winning hand. Germany's choice highlights the challenges of the nuclear renaissance. Even as technology advances, public perception and politics can pull in the opposite direction. Then there are the newcomers, nations stepping into the nuclear arena for the first time. Turkey, Bangladesh, and Egypt are building plants that will soon join the global grid, each driven by a mix of necessity and ambition. Bangladesh, for example, is a fast-growing nation with a power-hungry population. Its new reactors, built with Russian help, promise to bring stable electricity to millions, reducing reliance on fossil fuels. Egypt's project on its northern coast aims to bolster energy security in a region where power shortages are common. These emerging players are reshaping the nuclear map, proving that the peaceful atom isn't just for the old guard, it's a global opportunity. Countries like Indonesia are also in line, eager to harness nuclear power to fuel their rise in a warming world. What ties these diverse strategies together is a shared realization. Nuclear energy is no longer the risky gamble it once seemed. New technologies are making it safer and more practical. Small modular reactors, like those in the US, offer a nimble alternative to traditional plants. Thorium, as China and others are proving, brings efficiency and safety to the table. Even traditional uranium reactors are getting upgrades, with smarter designs that reduce risks and waste. The Renaissance isn't just about building more, it's about building better. Nations are learning from the past, blending innovation with caution to ensure nuclear power delivers on its promise without repeating old mistakes. This global revival is also a response to bigger forces. The world's thirst for energy is growing, driven by everything from electric cars to artificial intelligence. At the same time, the planet is sending urgent signals: rising seas, scorching summers, and violent storms. Nuclear power offers a way to meet these demands while cutting carbon emissions to near zero. Unlike wind or solar, which depend on weather, nuclear delivers steady, round-the-clock power. Unlike coal or gas, it doesn't choke the atmosphere. The Renaissance is a recognition that the peaceful atom, once sidelined by fear and economics, is now a vital tool in the fight for a sustainable future. The peaceful atom is far more than a workhorse for powering cities. While nuclear reactors light up homes and industries, their reach extends into realms that touch the very edges of human ambition. From healing the sick to exploring the cosmos, from navigating icy seas to dreaming of a world powered by the stars, nuclear technology is rewriting what's possible. As we stand on the cusp of a new atomic era, this is the story of how the peaceful atom transcends power plants, and a glimpse into the boundless future it promises. Let's begin with medicine, where nuclear technology is nothing short of a lifesaver. Imagine a patient facing a cancer diagnosis, the kind that defies surgery or traditional treatments. Nuclear medicine steps in like a silent hero, wielding radioactive particles to target disease with precision. Special compounds known as radiopharmaceuticals combine a guiding molecule with a radioactive isotope. The molecule seeks out cancer cells like a bloodhound tracking a scent, while the isotope delivers a burst of radiation to destroy the tumor, sparing healthy tissue nearby. This isn't science fiction, it's happening in hospitals worldwide, treating cancers of the thyroid, prostate, and blood, as well as heart and neurological conditions. The magic lies in the atom's ability to pinpoint problems, whether it's diagnosing a hidden tumor with glowing isotopes or blasting away malignant cells. Russia, a leader in this field, produces these critical isotopes, helping doctors save countless lives. This is the peaceful atom at its most human, turning the fearsome power of radiation into a tool for healing. Now, let's lift our gaze to the stars. The cosmos has always called to humanity, but getting there is no easy feat. Chemical rockets, the backbone of space exploration, are like sprinters, fast but limited, burning out quickly and struggling to carry heavy loads across vast distances. Nuclear technology offers a different path. Imagine engines powered by the same forces that drive reactors on Earth, capable of propelling spacecraft to Mars or beyond. These nuclear engines don't just burn fuel, they harness the atom's energy to generate thrust far more efficiently, opening doors to deep space missions that were once the stuff of dreams. Russia is leading the charge with a project called Zeus, a nuclear-powered space tug designed to haul massive cargo across the solar system. Picture it ferrying supplies to a future lunar base, or towing satellites into distant orbits. The United States is also in the game, developing nuclear thermal propulsion that could cut travel time to Mars dramatically. With nuclear power, the stars aren't just closer, they're within reach, promising a future where humanity isn't bound to Earth. Closer to home, the peaceful atom is conquering Earth's harshest frontiers. In the Arctic, where ice locks the seas for much of the year, Russia deploys a fleet unlike any other, nuclear-powered icebreakers. These massive ships, driven by compact reactors, carve through ice thicker than a house is tall, opening routes for trade and exploration. They deliver supplies to remote outposts, support scientific missions, and keep vital shipping lanes open in places where no other vessel could survive. Russia stands alone in this arena, with ships like Arktika and Sibir showcasing the atom's ability to tame the wildest environments. Each icebreaker is a floating power plant, its reactor humming with enough energy to break through frozen barriers and connect the world's northernmost reaches. This is nuclear energy not just powering homes, but forging paths where none existed before. These applications, medicine, space, and Arctic exploration, are proof that the peaceful atom is a versatile force, capable of solving problems far beyond electricity. But what lies ahead? The nuclear renaissance we're witnessing today is just the beginning, a stepping stone to an even grander vision. Scientists are looking to the stars not just for exploration, but for inspiration. Fusion energy, the process that powers the sun, is the holy grail of nuclear technology. Unlike today's reactors, which split atoms to release energy, fusion combines them, mimicking the reactions that make stars shine. The result? Near limitless power with no long-lived radioactive waste and no risk of meltdowns. It's the kind of energy that could run entire cities without a whiff of carbon or a speck of dangerous residue. The path to fusion isn't easy, it's like trying to bottle a piece of the sun, but the world is getting closer. In France, a massive international project called ITER is building a reactor to test fusion's potential. It's a slow, complex journey, with challenges like containing superheated plasma hotter than the sun's core. Yet every step forward brings us nearer to a future where energy is abundant, clean, and sustainable. Other projects, from private startups to government labs, are racing to crack the fusion code with hopes of commercial reactors in the coming decades. If they succeed, the peaceful atom will no longer be just a tool. It will be a cornerstone of a new world, where energy scarcity is a distant memory. This future isn't just about fusion. The technologies driving today's renaissance, thorium reactors, small modular designs, are already transforming the landscape. Thorium, with its safety and efficiency, could power nations with minimal waste, while compact reactors bring electricity to remote corners of the globe. Countries like China, Russia, and the United States are pushing these innovations, while newcomers like Turkey and Bangladesh join the nuclear fold, building plants to fuel their growing economies. The atom is no longer the exclusive domain of superpowers, it's a global promise, offering energy security and environmental hope to nations everywhere. The story of the peaceful atom began in a small Soviet town decades ago, when the Obninsk plant first sent electricity into the grid. That spark lit a fire that spread across the world, powering homes, healing bodies, and exploring new frontiers. Today, as we stand at the dawn of a new atomic era, that fire burns brighter than ever. The peaceful atom is more than a technology. It's a symbol of what humanity can achieve when we harness nature's most fundamental forces. From hospitals to the Arctic, from Earth to the stars, the atom is carrying us forward toward a future where the impossible becomes reality once again. In 2017, an international group of scientists discovered 7 Earth-like planets. Just imagine 7 rocky planets similar to Earth, and they all orbit a single star, which is only 39 light-years away. That's practically around the corner by cosmic standards. Astronomers are confident that very soon, using data from telescopes, they will be able to say for sure whether these planets have an atmosphere and if it contains water, vapor. And since water is a universal solvent in which the organic substances that build DNA molecules can mix, scientists may be able to show that conditions for life are found everywhere in the universe. It is possible that in the near future, the holy grail of planetary astronomy will be found, an Earth twin in open space. Around the same time, astronomers found another Earth-like planet, Proxima Centauri b, and it orbits the star closest to us, just 4 light-years from the Sun. That is, it is literally our cosmic neighbor, and it is also in the habitable zone, where liquid water can exist. All these discoveries are just a few new entries in a vast encyclopedia already containing over 5,000. World media reported another breakthrough in astronomy. Scientists obtained the first photograph of a black hole. Yes, that image where a red ring of gas spirals around a black shadow in the center. Billions of people have seen it. Black holes were predicted mathematically as a consequence of Einstein's equations over 100 years ago, and the photo confirmed that these initially unimaginable objects do indeed exist in space. By the way, this photographed black hole is monstrously huge. It is 6 billion times heavier than the Sun. Personally, its photo reminded me of the Eye of Sauron from The Lord of the Rings. Only this eye is real and the size of our solar system. To obtain this unique image, astronomers created a most powerful super telescope by combining data from comparison to the James Webb Space Telescope, which was launched at the end of 2021. In just its first year of operation, it sent back such images of distant galaxies that astronomers' jaws dropped. This is what the universe looked like over 13 billion years ago, shortly after the Big Bang. We see the very first galaxies, young, with irregular shapes. The light from them traveled to us several times longer than our planet has existed. And here is another image, no less interesting. The Ring Nebula. These are the remains of a dying star that shed its outer layers. Only thanks to the incredible clarity of the Webb images did the finest details become visible. Vortices and swirls of gas. Thus, astronomers saw for the first time what a star looks like at the moment of its death. And this is just the beginning. The Webb telescope will operate for many more years, regularly showing us new corners of the universe. And there are dozens of other observatories around the world and in space. All of them tirelessly scan the sky, collecting gigabytes of data to then assemble them into a unified picture of the universe. Is incredibly diverse. It has everything. From the smallest particles to giant clusters of galaxies, from the deserts of Mars to, possibly, oceans teeming with life on exoplanets. But do you know what is most surprising? All this magnificence obeys the same laws of physics. Laws that the human mind is capable of discovering and understanding. It's simply amazing how far we've progressed from primitive myths to modern astrophysics. By studying space, we better understand not only the universe around us, but also ourselves. After all, we are all children of the stars, literally. Every atom in our body was once created in the thermonuclear furnace. How did humans begin to build a picture of the world in their minds, starting only from simple observations? This adventure of human thought is described in the book by astronomer Sergei Vyazev. The Universe, A Journey Through Time and Space, and the book by theoretical physicist Michio Kaku, The God Equation. They have inspired this exploration. Let's together embark on this journey spanning thousands of years, from the primitive cosmology of ancient civilizations to the latest theories of the origin and evolution. Imagine yourselves as inhabitants of ancient Greece. If you had no knowledge of the world around you, how would you perceive the universe? You stand on solid ground, which, frankly, is flat, not counting mountains and valleys. Above you is a blue sky, with the sun, moon, and stars. Your life unfolds amidst wild nature, forests, steppes, rivers, and mountains. Every day, a dazzling bright circle, the sun, rises on the eastern edge of the sky. It gives the earth light and warmth, determining the rhythm of all living things. The sun makes its eternal journey, rising to its zenith and then descending beyond the horizon. It is the solar cycle that underlies the biological clocks of all inhabitants of the planet. As the luminary sets, the world plunges into darkness and cold. Myriads of stars appear in the sky, and their pattern remains unchanged from night to night. Observant earthlings group them into memorable patterns, constellations. This helps to navigate in space. 5 particularly bright stars change their position, tracing bizarre loops in the sky. They are called planets after powerful deities: Mercury, Venus, Mars, Jupiter, and Saturn. All these phenomena, well known to modern man, held many mysteries in antiquity. However, they were part of everyday life. Hunting, agriculture, and survival in general depended on them. The first thing people learned was the change of seasons. It turned out that the natural cycles associated with it were not a whim of chance, but rules. Spring was always followed by summer, but never by winter. And so, year after year, with the development of speech and abstract thinking, people began to delve deeper into the essence of the surrounding world. At first, they simply noticed sequential events. Sunset is followed by night. But then came an epiphany. It gets dark precisely because the sun has set. Day changes to night not by chance, but according to a strict the world consisted of 4 elements: earth, water, air, and fire. In China, wood and metal were added to this. All substances around were supposedly created from the mixing of these elements, and various gods controlled them. It was logical to assume that the earth was a flat disk, covered by a dome of the sky. In some places the disk is filled with water, but even under the water there's a solid bottom. Rain sometimes falls from the sky. Apparently there is a supply of water there. The sun and moon move across the sky, and the stars look like holes in the celestial vault, letting in external light. The same picture of the world was described in the Old Testament. God created the firmament, separating the earthly waters from the heavenly ones. On the firmament he placed the luminaries, the sun, moon, and stars. Few disputed these ideas, as they coincided with the visible picture. Why not? There was also a belief that the massive earth rested on some supports: elephants, turtles, bulls, and what have you. The movement of these creatures explained earthquakes. The earth could float in a world ocean, or be attached to the sky by chains. A Muslim myth depicted a complex structure of an angel, a bull, a vessel, and a fish on which the earth rests. According to a Slavic legend, an oak tree and whales in a fiery sea played the role of supports. This is an important point. Authors of cosmological concepts could pile one support for the earth on top of another, but somewhere this process had to stop. Otherwise, the supports would multiply indefinitely. Sooner or later, thinkers realized that the will of higher powers was indispensable here. Although if divine intervention was still required, it was more logical to resort to it immediately. Making the earth simply float in space was the ancient Greek philosopher Anaximander in the 6th century BC. In his model, the cylindrical earth simply hung motionless in the center of the cosmos. The explanation was brilliantly simple. The earth had no reason to move in any direction since it was already in the center. To realize that the huge earth with all its continents and oceans could freely rest in the void was a huge intellectual breakthrough. For however absurd this thought might be for the common person, it is still more reasonable. Anaximander was the first to suggest that celestial bodies are at different distances from Earth. In his opinion, a certain primordial substance first existed, a pairon. It separated into a cold core and a fiery shell. From the heat, the shell disintegrated into several rings. In the nearest ring were stars, holes through which fire was visible. In the next ring was a larger slit, the moon. And in the farthest ring was a hole the size of the Earth, that is, the sun. At the very heart of the universe, the Earth arose, resembling a flattened cylinder. Its surface was covered with moist primeval ooze, in which a real miracle occurred. The first living creatures originated in it. They resembled fish and, evolving, came out onto land, And from these amazing creatures, the first humans were formed, leaving their fish cradles. Essentially, this was the first geocentric system of the world. Of course, all this is no more than a beautiful fairy tale. But you must agree, for those times it was impressive. They did without gods, explained the earth, life, and man. But alas, this hypothesis could neither be proven. Anaximenes and Heraclitus developed this idea, adding new details. They were united by a materialistic view of the universe. The world explains itself without reference to gods. Heraclitus, for example, proclaimed sight and hearing as the main cosmology of the great mathematician Pythagoras. In the 6th century BC, Pythagoreans believed that the universe was governed by the mathematical harmony of whole numbers. Thus, Pythagoras discovered that the sounds of an octave are born when a string is divided in ratios of 1 to 2, 2 to 3, 3 to 4, and so on. That is, musical intervals are set by simple numerical ratios. For Pythagoras, this meant that pure mathematics lay at the heart of the cosmos. Hence his famous, all is number. How did Pythagoras envision the universe? In the center of the universe floated a mysterious central fire, Hestia. Around it, the Earth, Moon, Sun, and 5 known planets orbited. Between the Earth and Hestia circled a mysterious anti-Earth, forever hiding the central luminary from us. Beyond Saturn followed the sphere of fixed stars. There were a total of 10 celestial spheres, an ideal number for Pythagoras. It is noteworthy that Pythagoras did not think that celestial bodies fly in a void. They were supposed to be attached to giant crystal spheres, nested one inside the other. Rotating at different speeds, these spheres carried the planets and stars, and also produced music, a specific note for each. We do not hear this harmony of the spheres only because we were born in it and perceive it as silence. Of course, Pythagoras' system was also speculative, like all the previous ones. Spherical Earths, crystal spheres, anti-Earth. All these are no more than guesses, but here for the first time the planets were named in the correct order, and it was shown that the Earth is not the center of the world, but merely one of the celestial bodies revolving around something else, even if not the sun. Pythagoras' followers even explained the change of day and night by the Earth's rotation. This is practically Copernicus. As early as 25 centuries ago, the best minds of humanity began to seriously ponder the structure of the cosmos. Albeit purely intuitively and without reliance on experience, insights deeper than tales of Earth on whales were made even then. What unites all these theories of the ancient world, from the biblical to the Pythagorean? You've probably guessed it. That's right, they were mostly made up. Well, yes, although they were based on observations, much was conjectured. In the end, all of this turned out to be incorrect. Neither a flat Earth, nor a celestial firmament, nor crystal spheres admitting to distinguish truth from fiction. Apparently, it was the emergence of critical thinking, upon which the scientific method grew. Humans began to analyze their own ideas, asking themselves, why do I think so? Can I think differently? What if lightning is not Zeus's anger? It was critical thinking that became the engine of civilization's progress. Take, for example, the ancient texts of Egypt and Babylon. There was nothing like mathematical proofs there. The very concept was absent. Proofs appeared in ancient Greece more than 2,500 years ago, probably thanks to the birth of democracy. In disputes among equal aristocrats, logic, different points of view, and their argumentation were required. The one with the better arguments won, not the one with a laurel wreath on his head. The transfer of the practice of proof to mathematics led to the appearance of theorems. Thales was already proving the statement about the equality of angles at the base of an isosceles triangle. Mathematics was considered a noble pursuit, a kind of elite club. It is not surprising that the Greeks soon developed. Aristotle was one of those who applied a scientific approach to the structure of the universe. Studying the moon, he understood the nature of its phases. The moon is a sphere onto which sunlight falls. Observing the moon occulting Mars, Aristotle concluded that planets are located farther than the moon and stars farther than the sun. But that's not all. Aristotle also had 3 arguments in favor of the Earth's sphericity. Firstly, when a ship moves away from the shore, its lower part disappears first, then the middle, and only then the sail. This is possible only if the surface of the sea is convex. Secondly, lunar eclipses occur when the Earth is between the sun and the moon, and the Earth's shadow on the moon always has a rounded shape. Thirdly, when an observer moves north, the North Star rises towards the zenith. This again indicates the curvature of the Earth's surface. Based on these facts, Aristotle logically impeccably proved that the Earth has the shape of a sphere. True, he was slightly mistaken in thinking that the Earth was the center of the universe, but here too he proceeded from observations. If the Earth moved around the sun, he reasoned, then we would see the displacement of stars. But stars are so distant that these tiny displacements were measured only in the 19th century. In Aristotle's time, Aristotle's ideas were embodied in Ptolemy's system. He wondered how to reconcile theory with what we see in the sky. He had to develop a complex system of epicycles, that is, circles along which celestial bodies moved, and deferents, other circles along which the centers of the epicycles moved. Yes, the system was exactly as complicated as it sounds. Epicycles in deferents, deferents in epicycles. Perhaps Ptolemy invented not only the geocentric system, but also the world's first Matryoshka doll. The radii and speeds of movement along the circles were chosen so that the result corresponded as much as possible to observations. For a better match, the system had to be stuffed with dozens of epicycles. Despite its contrived nature, Ptolemy's system excellently predicted the position of planets for a year ahead. And Ptolemy did not just consider the Earth stationary for no reason. He was a brilliant scientist and knew about centrifugal force and inertia, but without precise formulas and experiments, he could not assess their effect. He reasoned thus: if the Earth rotated, then all falling objects and clouds would lag behind, carried by inertia. A stone dropped into a deep mine would hit the wall. 1,700 years later, Benzenberg's experiment proved that this effect does indeed exist due to the planet's rotation, albeit very small. Ptolemy's system was based not on guesses, but on strict logic and observational data, and this distinguished it from previous world pictures. Eventually, science itself, by testing and perfecting itself, later refuted this model. But before that, Ptolemy's system dominated observations made by the Greeks 2,000 years ago. It followed that a spherical, stationary Earth was at the center of the world. Did no one question this? There were such daredevils, for example, Aristarchus of Samos, who long before Ptolemy proposed a method for measuring distances to the sun and moon. Observing the moon in its first or last quarter phase, when we see exactly half of its disk, Aristarchus reasoned as follows: the angle between the Earth-Moon and Moon-Sun directions is a right angle. Therefore, the ratio of the Earth-Moon distance to the Earth-Sun distance is equal to the cosine of the angle between the directions to them, and it can be measured. Having made such measurements, Aristarchus found that the sun is 20 times farther than the moon. In reality, it is 400 times, but for those methods it was a decent estimate, and since the apparent sizes of the sun and moon are approximately equal, the sun must be 20 times larger than the moon. By comparing the apparent sizes of the Earth's shadow on the moon during eclipses, Aristarchus calculated that the Earth is about 3.5 times larger than the moon, which is close to the truth. From this, it followed that the sun is about 6 times larger than the Earth, that is, hundreds of times larger by volume. But the most interesting part is ahead. The colossal size of the sun led Aristarchus to the idea of a heliocentric system of the world. It is more logical that the huge sun would be at the center and the smaller Earth would revolve around it. Confirmation came from changes in the brightness of Mars, inexplicable in the geocentric model. The displacement of stars during Earth's movement is not visible simply because they are incredibly far away, Aristarchus asserted, and he was absolutely right. But at that time, his hypothesis could not yet compete with the well-ordered and after the decline of ancient civilization and the onset of the Middle Ages. The understanding of the universe's structure not only did not develop, but also lost its previous achievements. Christianity brought a different spirit of the times. The need for research into the world beyond the Bible was questioned. The works of ancient thinkers were often destroyed. In the Library of Alexandria, they were burned to the ground, along with thousands of priceless books and manuscripts. Want to ask an inconvenient question? Welcome to the stake. The main picture of the world for Christians in the 6th century became the primitive scheme of Cosmos Indicopleustes, a flat, quadrangular Earth, surrounded by walls and covered by a solid celestial vault. Night falls when the sun hides behind a high northern mountain. The idea of a spherical Earth was initially ridiculed. How can people on the other side walk upside down? Subsequently, Aristotle's teachings were accepted by the Church, but selectively. The idea of the Earth's central position as God's main creation fully corresponded to biblical notions. And why not? It's logical, isn't it? The Earth is flat and rests in the center of the world. The Earth is the crown of God's creation, no less. All according to the Bible, you can't find fault. The spirit of inquiry, Aristotle's call to study the world through observation, was forgotten. Scientists' treatises were simply memorized without analysis or criticism. Independent thought was not encouraged and was under threat of accusation of heresy. It is not surprising that not a single astronomical discovery was made in Europe. Did astronomy move from a standstill? And do you know who had the courage to revive the heliocentric idea? A priest? Imagine Nicholas Copernicus sitting in a monastery, studying ancient folios, and at some point it dawns on him, wow, this is it all fits. The sun is at the center and the Earth revolves around it. The Earth, moreover, rotates on its axis. All this immediately explained the loop-like movements of the planets. But Copernicus was in no hurry to shout about his discovery from the rooftops. Of course, he spent 40 years to verify everything and leave no loopholes for criticism. He followed Ptolemy's structure but used fewer epicycles in combination with deferents instead of cumbersome ones. Most importantly, Copernicus swapped the Earth and the Sun, making the latter the center of the system. The planets were attached to transparent solid spheres, nested one inside the other. All the stars were on the largest sphere surrounding the solar system, just like wallpaper on walls. In general, Copernicus's work was quite a tome. Not everyone could master it, and its predictions were worse than Ptolemy's system, but his main ideas instantly spread throughout Europe. It was a real breakthrough. It's just a pity that Copernicus himself did not live to see the publication of his work. The man was not allowed to enjoy, which received the name Copernican Revolution, was truly revolutionary. Just think about it. The Earth moved from the center of the universe to somewhere on the outskirts, becoming just one of many planets. Humanity lost its privileged position in the world. What a blow to self-esteem. This transition dragged on for many years and was not easy. It would seem that no new evidence in favor of heliocentrism appeared then. All the arguments cited by Copernicus had already been voiced earlier, for example, Methuos by Aristarchus of Samos. The Catholic Church initially reacted calmly to the heliocentric model, seeing it only as a convenient method of calculation, but soon it sensed an unpleasant heretical whiff in the idea of displacing the Earth from the center of the universe. The situation was especially aggravated by the fervent supporter of Copernicus's ideas, Giordano Bruno, who openly criticized church dogmas. Let's just say he added fuel to the fire. In his opinion, the universe is infinite and filled with many worlds similar to the solar system. Stars are distant suns around which planets also revolve, possibly inhabited. Such bold ideas of a multiplicity of worlds could not please the church. The outcome is sad. In 1600, Bruno was burned at the stake. Copernicus's work on the revolutions of the celestial spheres was included in the Index of Forbidden Books in 1616. It seemed that heliocentrism... In 1609, Galileo Galilei, inspired by the Dutch spyglass, built a telescope and pointed it at the sky. Discoveries poured in one after another. Galileo discovered that Venus has phases, like the moon, which means it orbits the sun. Jupiter's moons clearly orbited that planet, not Earth. These were irrefutable proofs of the validity of the heliocentric system. So why did Copernicus's idea eventually win, despite all the power of the Church? It seems it was due to another change in the spirit of the times. The life of Europeans in the 17th century was full of hardships and upheavals. The familiar medieval order was collapsing. Religious wars were raging. Epidemics were rampant. You must agree, in such an environment, it is difficult to feel like the pinnacle of creation, living in the ideal center of the universe. Rather, the Earth, ravaged by disasters, turned out to be a godforsaken periphery. Far from perfection, the place in the center of the universe was more suited to the sun, the ideal, eternal source of light and heat. Thus, public consciousness, gripped by crisis, turned out to be psychologically ready to accept and logical picture of the world. There was still one more obstacle. The idea of the uniform motion of planets in perfect circles. It was precisely to explain the visible deviations from it that ancient and medieval astronomers constructed unimaginable intricacies of epicycles and deferents, and even Copernicus could not completely abandon them. Only at the beginning of the 17th century did the brilliant Johannes Kepler, after analyzing the most precise data from astronomer Tycho Brahe on the motion of Mars, discover his famous laws. It turned out that planets move around the sun not in circles but in ellipses. Moreover, the speed of a planet is not constant. The closer to the star, the higher it is. Kepler's laws described the observed movements of planets with amazing accuracy, without any of those cycles and epicycles, confirming and supplementing Copernicus's heliocentric system. It is not without reason that they are often called the final chord of the Copernican revolution. But the pinnacle of this revolution was the concept of the infinity. Nicholas of Cusa argued that in an infinite universe, there can be no absolute center, neither in the form of the Earth nor the Sun. He Pascal the existence of countless worlds. Giordano Bruno developed these ideas, stating that only an infinite universe with an innumerable number of star worlds, many of which may also be inhabited, can correspond to the greatness of the Creator. Imagining infinity is easier than it seems. We encounter it from childhood. For example, there is no largest prime number, because one can always be added to any number. A spacecraft will never hit a wall with the inscription, "End of the world," and no matter how much time passes, the next moment will always come. In my opinion, it is more difficult to imagine a finite universe than an infinite one. Such a picture of the world broke the usual ideas about solid celestial spheres and the dome of fixed stars, because infinite space does not need material support. In essence, critical reflection showed that if the Earth is capable of freely floating in space, then why can't other celestial bodies float in the same way? Even in the first pictures of the world, it was necessary to introduce God's will, simply to interrupt the endless series of celestial spheres or cosmic turtles. So here too, no matter how the church suppressed free thought, the idea of an infinite universe inevitably sprouted. For a long time, people were interested in the question of what forces set celestial bodies in motion. Some believed that the luminaries move by themselves, being alive. Others believed that spirits, angels, or gods controlled them. But centuries passed, and all these supernatural explanations somehow lost their persuasiveness. People got used to the idea that impersonal natural forces, the laws of nature, operate in the world. Kepler, who discovered the laws of planetary motion, suggested that the speed of a planet decreases with distance from the sun because the source of the driving force is contained within it. William Gilbert, a contemporary of Kepler, studied magnetism and suggested that the Earth is a giant magnet. This was indicated by the behavior of the needle of the compass, invented by Gilbert. And magnetism is a universal force in the universe. In the early 17th century, it was even discussed whether the Earth rotates due to magnetic forces and whether the moon affects tides through magnetism. In 1609, Kepler went even further. What if the sun is also a magnet, and its rotation creates a vortex in the ether, causing planets to move around the sun slower the farther they are from it? Descartes went even further, imagining the universe as a multitude of ethereal vortices with stars at their centers. Although these ideas turned out to be incorrect, it was later confirmed that the sun is indeed a magnet, and its magnetic field rotates with it. The nature of the planets governing the universe was revealed by the brilliant Isaac Newton. He guessed that the force holding the moon in orbit and the force attracting a thrown apple to the Earth are one and the same. After all, if the moon suddenly stopped, it would fall to Earth like an apple. It's just that the moon has a huge orbital velocity, thanks to which it constantly, as it were, misses the Earth. Can we turn an apple into a moon by giving it a high enough speed? Newton understood. Yes, easily. Continuously falling, it will orbit the Earth, becoming its satellite. Imagine a cannon firing horizontally from a high mountain where there is no air and friction. If you increase the speed of the projectile, it will fall to Earth farther and farther from the cannon. At a certain speed, the projectile will not fall, but will continuously orbit the Earth in a circular orbit like a satellite. This speed was called the first cosmic velocity. If the projectile is launched at a speed higher than the first cosmic velocity, it will begin to move in an orbit in the shape of an elongated ellipse. With increasing speed, this ellipse will become more and more elongated. When the speed reaches the second cosmic velocity, the projectile will leave the Earth forever. Thus, Newton discovered the universal law of gravitation, according to which gravitation is noticeable when at least one mass is enormous, like that of the Earth, but it acts between any bodies, obeying a strict formula. Studying the motion of the moon, Newton mathematically derived this law, and then it turned out that all three of Kepler's laws are simply a consequence of it. The theory of gravitation worked like clockwork, allowing orbits of planets and spacecraft to be calculated with enormous accuracy. Establishing Newton's theory was played by comets. Analyzing their movement, astronomer Edmund Halley established that the trajectories of comets are greatly elongated ellipses that intersect the orbits of planets. If crystal spheres existed, comets would inevitably collide with them, but nothing of the sort was observed. Thus, comets shattered the crystal spheres to smithereens. As a result, by the 18th century, enlightened humanity accepted a new picture of the world. The universe was seen as an infinite space, inhabited by a multitude of stars with planetary systems similar to our solar system. A single law of gravitation acted throughout the cosmos, and time flowed uniformly everywhere. Of course, mysteries remained. For example, why do planets rotate in one direction around the sun, and also almost in the same plane, unlike the chaotic movement of comets? Unable to find an explanation for this, even Newton resorted to the idea of divine design. Telescopes, astronomers obtained more and more data about distant objects in the universe. And what did they see? It seemed that nothing globally changes there at all. On Earth, seasons changed. Planets and comets circled around the sun. Stars twinkled in the distance. The cosmos looked stationary, as physicists say, unchanging over time. Perhaps individual stars faded, but new ones lit up to replace them, and many believed that it would always be so. The universe will remain eternally unchanged, like an ocean where waves constantly replace each other, never leaving the surface, calm. Of course, even in the Middle Ages, thinkers allowed that the cosmos could evolve, but this idea was not in trend. Astronomers were rather trying to understand the properties of celestial bodies. Based on the postulate of the immutability, it was necessary to find out the distance to the stars. How to do this became clear back in antiquity. If you measure the position of a star many, many times over a year, then due to the Earth's revolution around the sun, the points on the celestial map will form a small ellipse, the star's annual parallax. The smaller it is, the farther the star. Alas, for a long time, parallax could not be detected even by great astronomers like Kepler and Herschel. The stars stubbornly remained motionless. Supporters of geocentrism rejoiced. Aha, there's an argument for a motionless Earth for you. But Copernicus and his followers did not give up and rightly objected. No, the stars are just incredibly far away. Only in 1838 did Friedrich Bessel, using the most precise Fraunhofer telescope, finally measure the parallax of one of the stars. It turned out to be at a distance of 10 light years, that is, hold on tight, 90 trillion kilometers. Soon Struve and Henderson made similar measurements. Thus a breach was made in the wall that had for centuries hidden the stellar distances from us. It turned out that even the nearest stars are light years away. Alpha Centauri is 4.3 light years away. Light takes 8.5 years to reach Sirius. But how far then does all stellar space extend? A bright band girdling the entire sky. It was visible from both hemispheres of the Earth, which indicated that the Sun and other planets are inside a huge flat system of stars. This was called a galaxy. Democritus had already guessed that it was a cluster of stars, but only Galileo's telescope confirmed his correctness. I observed the nature and substance of the Milky Way. With the help of a telescope, it was possible to observe it in such detail and with such visual clarity that all disputes were resolved. The Milky Way is in fact nothing more than a mass of countless stars gathered in clusters. In the 17th and 18th centuries, astronomers using telescopes discovered many faintly glowing nebulous patches in the sky, which they called nebulae. It turned out that matter can be organized not only into stars and planets, but also into gigantic volumes of diffuse matter. Thomas Wright was the first to suggest that the stars of the Milky Way form a giant flat disk. Herschel and his sister Caroline scrupulously counted the stars all over Thesky. The result of their 20-year labor was a map of the galaxy, which for the first time showed its disk-like shape. But it turned out that the Milky Way is much more galaxy is a flat, unwinding spiral of hundreds of billions of stars with a bar in the center. 2 main arms branch into as many as 5. The diameter of this behemoth is 100,000 light-years, and its thickness is about 1,000. The Sun is located on the periphery of the galaxy, 26,000 light-years from the center, where a supermassive black hole of 4 million solar masses is hidden. So if you ever feel insignificant and peripheral, remember, even the Sun is just a provincial star on the outskirts of a galaxy. But this does not prevent it from being the center of our world and the source of life on Earth. But is our galaxy identical to the entire universe? After all, other nebulae of different forms are visible in the sky. Some, even in powerful telescopes, look like gas clouds, not clusters of stars. William Parsons, in his giant telescope, discerned among them spiral ones, similar to the structure of the Milky Way, only very distant. But where are they? In our galaxy or observing the Andromeda Nebula? The previous method of determining distances no longer worked here. Too far. However, astronomers found a new way thanks to a special type of star called Cepheids. These are stars that regularly change their brightness. They become brighter, then dimmer, and so on in a cycle. Astronomer Henrietta Leavitt in 1908 discovered that the maximum luminosity of a Cepheid is directly related to the duration of its brightness change cycle. This means that by knowing the period of a star's brightness change, one can accurately determine how bright it is at its brightest moment. This discovery allowed astronomers to measure the distance to stars that are very far from us. Hubble found several Cepheids in the Andromeda Nebula and calculated the distance to them. It was 2 million light-years, that is, 20 times the size of our galaxy. Thus, it was proven that the Andromeda Nebula is not some distant corner of the Milky Way, but a completely different galaxy, possibly similar to ours. For the first time, it became clear that the visible universe, French philosopher Auguste Comte made a strong assertion implying certain knowledge about stars was unattainable. But science coped with this too, thanks to the emergence of astrophysics. What can we observe and study on Earth from distant stars? Only light. Newton had already shown that sunlight contains waves of different lengths, from red to violet. Astrophysicists learned to decompose this light into a spectrum using spectroscopes, and the shape of the energy distribution curve in this spectrum allows for the precise determination of a star's temperature according to Wien's displacement law. The shorter the wavelength, the hotter the star. If the energy peak is in the blue region, it means the star's temperature is around 20,000 degrees Celsius. Our sun has its maximum in the green region, which corresponds to 6,000 degrees. Red stars are cooler, around 3,000, and these conclusions do not depend on the distance to the star. Experienced astronomers can even estimate a star's temperature by its color with the naked eye. But how can one be sure that the temperature obtained from the spectrum is correct? After all, you can't fly to distant stars with a thermometer, or can you? The laws of physics are universal. The relationship between the shape of the spectrum and the temperature of the source has been tested hundreds of times in laboratories. Mathematics and logic in physics work unequivocally. If the conclusions of a theory agree with experiments, then the theory is correct. And astrophysical methods yield results that also converge and predict new phenomena. If there were an error in analysis, also allows us to learn the chemical composition of stars from the dark absorption lines. Each element leaves a characteristic set of lines in the spectrum, its own fingerprint. The presence of lines of hydrogen, iron, calcium indicates the presence of these elements in the star's atmosphere. Their quantity can be estimated from the depth of the lines. By the way, this is precisely what allows us now to study the Doppler effects played a huge role. It turned out that the lines in the spectrum of light depend on the conditions at the place from which the light originated. Experiments showed that some absorption lines split into 2 or 3 under the action of a magnetic field in the light source. This phenomenon was named the Zeeman effect in honor of the physicist Peter Zeeman, who discovered it, one of the first Nobel laureates in physics. The detection of the Zeeman effect in the spectra of sunspots led to the discovery of magnetic fields on the sun. In 1842, physicist Christian Doppler also discovered an effect named after him. He noticed that the pitch of a whistle from an approaching train seems higher, and from a receding one, lower. This was confirmed by an experiment where an orchestra played on a moving platform, and people with musical hearing stood on the platform and detected the differences. A spectacular experiment, but what does it have to do with astronomy? French physicist Armand Fizeau proved that the Doppler effect applies not only to sound, but also to light. If a light source is moving away from us, the lines in its spectrum shift towards the red end, and the speed of recession can be determined by the magnitude of the shift. Measurements showed that the lines in the spectrum of the eastern edge of the sun have a blue shift, and the western edge, a red shift. This confirmed the sun's rotation and allowed its speed to be determined, which coincided with data from the 20th century. Astronomers had a powerful arsenal of methods for studying distant celestial objects. Huge telescopes equipped with spectrographs allowed for the determination of the composition, temperature, velocities, magnetism, sizes, and masses of stars, not to mention the orbits and properties of even invisible planets around other suns. It would seem that the rapid development of science, mathematics, physics, chemistry, and along with them, astronomy, had finally given humanity a clear picture of the world, in which only details remained to be clarified. But already in the 19th century, scientists began to receive signals that something was wrong with the picture of an eternal gravitational paradox. Think about it. If stars attract each other, why don't the distances between them change? It was believed that the attraction of an infinite number of luminaries from different sides was balanced, but upon closer examination, this is not so. Gravitation only works to bring masses closer, and repulsion was not known then. This means that stars must inevitably fall onto each other, and the closer they are, the faster they will do so. Over infinite time, they would have long ago merged into one super-dense lump, yet galaxies are scattered over enormous distances with no signs of convergence. Stars in a galaxy move fast enough not to fall into its center, a supermassive black hole. Their speeds exceed the first cosmic velocity. Everything that moves slower has already fallen into the center of the galaxy, and bodies flying faster than the second cosmic velocity have flown away. Our objects with speeds between the first and second cosmic velocities have remained in elliptical orbits, but neighboring galaxies, in most cases, do not move fast enough to avoid merging. Thus, the Milky Way and the Andromeda Nebula are flying towards each other, and in billions of years, they will inevitably merge into a supergalaxy. The question arose, if the universe is infinite and eternal, why haven't all massive objects merged into one huge lump yet? After all, over infinite time, any process should have time to complete. This paradox showed that something doesn't add up in the picture of an Hilbert's photometric paradox. Imagine you are in an infinite forest. Wherever you look, there are trees, right? So in an infinite universe, we should see stars in every direction. Then the whole sky would shine brighter than the Milky Way without a single dark spot. Even cosmic dust wouldn't help. Over eternity, it would have heated up from starlight and started glowing itself. It turns out that the black sky is just holes between the stars. And that means their number is not infinite. At the turn of the 19th and 20th centuries, a real revolution took place in science. The discovery of X-rays, capable of penetrating opaque objects, overturned many provisions of classical physics. The phenomenon of radioactivity was identified. Scientists delved into the deep structure of matter and figured out the structure of atoms, which Democritus had brilliantly guessed at. It turned out that atoms consist of heavy, positively charged nuclei around which light, negatively charged electrons swarm. In the nucleus itself are protons and uncharged neutrons. Amazingly, new scientific instruments made it possible to detect individual electrons smaller than 1/100 billionth of a centimeter and even study their properties. Was unraveled. That's progress. James Clerk Maxwell created the theory of electromagnetism, showing the inseparable connection between electricity and magnetism. He reduced all known properties of electromagnetic phenomena to 4 equations. From them followed something amazing. Light is an electromagnetic wave traveling in a vacuum at a constant speed. But what then oscillates in a vacuum? The concept of a field had to be introduced. A magnet or charge seems to endow every point in space with a special property, to attract or repel. And these properties of the electromagnetic field are described by Maxwell's equations. And also, these equations contained a mysterious constant c, the speed of electromagnetic waves in a vacuum. Amazingly, it was exactly equal to the speed of light. Thus, the guess that light has an electromagnetic nature was brilliantly confirmed. This discovery simply blew minds. The universe turned out to be permeated by an invisible network of fields, electromagnetic and gravitational, and the propagation of light finally received a clear explanation. Photons are quanta of the electromagnetic field. Its waves are the very light that brings us all information about distant galaxies. The world turned out to be invisibly richer and more complex, which presented the speed of light as a fundamental constant, deeply impressed the young Albert Einstein. In 1905, he published an article outlining the basics of the special theory of relativity. Motion is relative. All physical laws look the same for observers moving uniformly and rectilinearly, regardless of speed. And the speed of light in a vacuum is constant in any frame of reference. That is, according to Einstein, all laws of physics are the same for observers moving uniformly and rectilinearly, and the speed of light is always constant. It seems simple, but the consequences? Phew, listen carefully, this is intense. For example, if you throw a ball on a train in the direction of its movement, the speed of the ball is equal to the sum of the speeds of the train and that ball. By this logic, a laser beam emitted from the side of a starship should propagate faster than the speed of light due to the ship's speed. But no, the laser beam will travel at the same speed of light as for a stationary observer, no faster. This means that time and distance flow differently for them. To explain this, Einstein suggested that clocks on the starship run slower and the ship itself contracts in the direction of motion. The crew would notice nothing. For them, everything would be as before. Nonsense? Not at all. Experiments confirm this. The speed of light is the same for approaching and receding stars, and clocks on satellites really do lag behind those on Earth. It turns out the world is not at all like Newton's, where time flows the same everywhere. For Einstein, space and time are relative. They depend on speed. He generally considered them a single whole, a 4-dimensional continuum, and only all 4 coordinates together, 3 spatial dimensions and 1 temporal, completely determine the location of an event in the universe. Now you know the secret of eternal youth. You just need to fly at the speed of light. The theory of relativity showed that the speed of light is the limit. It cannot be exceeded, not at all. For example, if you weigh 70 kilograms and develop a speed of 90% of the speed of light, you will weigh 160 kilograms. If 99%, then about 500 kilograms. And if you accelerate a little more, less than 1% to 99.99%, then your mass will already be 5 tons. As you approach the speed of light, mass increases to infinity, so it's impossible to accelerate further. Only gravitational waves or massless particles like photons always travel at the speed of light. Finally, but Einstein for them, lifted the veil of mystery over the nature of energy. It turns out it's not just about mechanical work. There's also thermal energy and the energy of particle interaction. As Richard Feynman, whom you know well, aptly put it, there's a certain quantity called energy, which does not change during any transformations occurring in nature. This is essentially a mathematical principle stating that there is some numerical quantity that does not change under any circumstances. This is by no means a description of the mechanism of a phenomenon or something concrete. It simply notes the strange circumstance that one can calculate some number and then calmly watch nature perform any of its tricks, and then calculate this number again, and it will remain the same. Einstein derived the famous formula linking the total energy of a body and its mass. E equals mc squared. Its meaning is that mass is, in essence, a reserve of energy. And an incredible one at that. Even in a tiny piece of matter, there is energy like in an atomic bomb. 1 gram is 20 kilotons of TNT. True, to release this energy, annihilation is needed. This is when a particle meets an antiparticle, and they turn into pure radiation. Mass disappears, but a lot of photons appear. By the way, 30 years after Einstein, his formula explained where stellar energy comes from. It turns out that in the depths of stars, hydrogen turns into helium. But the mass of the resulting helium is slightly less than that of the original hydrogen, and this excess mass becomes radiation, starlight, Every second, millions of tons of hydrogen in physics was brought about by the general theory of relativity. Its essence is simple, principle. Space-time and matter are inextricably linked. Masses curve space, and it affects the motion of bodies and the passage of time. It sounds wild, but it's true. Imagine space as a trampoline. Place a heavy ball on it. It will bend the surface. The heavier the ball, the stronger the bend. Now roll small balls across the trampoline. They no longer roll straight, but go around the massive object in an arc, just like planets around a star. Due to the curvature of space, light rays also bend near massive bodies. Einstein predicted this, and already in 1919, during a solar eclipse, astronomers noticed that the stars around it had shifted slightly. The moon noticeably curves space. This is absolutely counterintuitive, but the geometry of the universe is indeed not Euclidean. And another surprise from Einstein, time flows differently in different places. The stronger the gravity, the slower clocks run. On Earth, time lags slightly behind lunar time. It's hard to believe, but ultra-precise experiments have confirmed this. For example, Gennady Padalko, the record holder for time spent in orbit, aged 0.02 of a second less than his twin on Earth over 879 days in space. Of course, the difference is minuscule, but it exists. It turns out that space-time is not a frozen stage, but a living, moving actor. Masses bend space, and it changes the motion of bodies and the passage of time. Einstein instantly became a rock star. "Revolution in science!" proclaimed the Times headline. "The greatest achievement of human thought," echoed Joseph John Thomson. But you know what's interesting? General relativity did not cancel Newton's physics, but supplemented it. At low speeds and scales, their predictions hardly differ. But the stronger the fields and the faster the movements, the more important it is to consider Einstein's theory. He himself said that his idea is a new step from which old physics is seen as a special case. In short, Einstein didn't just rock the boat for no reason. His ideas still change our view of the world. Mass, energy, space, and time turned out to be inextricably linked in a single dancing tangle. And we are a part of it. So next time you look at the stars, astronomer John Michel wondered what would happen if a star was so huge that the escape velocity from it equaled the speed of light. Calculations showed that in such a case, even light could not leave its surface. Michel called them dark stars. But at that time, scientists lacked the knowledge to develop this idea. After all, no one even knew the exact speed of light. Only in 1916 did Karl Schwarzschild, inspired by Einstein's theory, find an exact solution to his equations for the simplest case. First, it is meant being a point particle. This approximately described the gravity of a spherical star, and Schwarzschild's solution led to unusual conclusions. It turned out that a supermassive star is surrounded by some magical sphere, now called the event horizon. Outside, the star's gravity is familiar, but inside the sphere, an object that has fallen there can no longer return. Approaching the horizon, an observer would see captured light circling the star, and just before the horizon, it would be torn apart by immense gravity. From the outside, it would seem that time inside a ship at the horizon slows down and stops, although for the astronauts themselves, nothing unusual would happen except for the sad fate of being torn apart, of course. For a long time, everyone thought this was just science fiction, but in 1939, Robert Oppenheimer and his student Hartland Snyder proved that black holes can really appear from massive stars that have run out of fuel. They simply collapse under their own gravity and turn into a black hole. Remnants of giant stars and supermassive monsters at the centers of galaxies. Astronomers have even found a black hole of 4 million solar masses right in the center of our Milky Way. If not for the dust clouds, it would shine brighter than the moon in the sky. Terrifying. But physicists didn't stop there. They took quantum theory and applied it to black holes. Stephen Hawking showed that an ideally black hole violates quantum uncertainty, which means it must slowly emit radiation. It turns out that a vacuum is not emptiness, but some kind of quantum broth, and in the powerful field of a black hole, virtual particles are born in it. One can fall into the hole, and the second can fly away. This is Hawking radiation. Thus, black holes evaporate. Black hole has absorbed go. In 1963, Roy Kerr found a solution for a rotating black hole. It turned out that it collapses not into a point, but into a ring. Passing through it, we enter a parallel universe, or another region of ours, as if through a wormhole. These tunnels in spacetime can connect distant regions or even different universes. Theoretically, one can move through them faster than light, without violating the laws of physics. But if wormholes ever give us the opportunity to instantly travel across the galaxy, will they be able to throw us an arrow? Then for Einstein it more resembled a winding river, flowing at different speeds in different places. If we can move in 3 spatial dimensions, why not travel into the 4th, time? What if there are whirlpools in this river of time that throw us into the past? And can it split into 2 streams, creating parallel universes? Yes, special cases of the theory of relativity allow for such possibilities. Hawking was so struck by this idea that he proposed the chronology protection conjecture. This is an undiscovered law of nature that prohibits time travel. Otherwise, as he joked, where are the crowds of tourists from the future at all important historical events? Just imagine what chaos would ensue if we had a time machine. Everyone would suddenly get rich on Bitcoin, tell Nikola Tesla about wireless charging, try to convince Van Gogh not to cut off his ear. This is perhaps the most useless action one could imagine, but then paradoxes arise. What if you kill your own grandfather in his childhood? How did you even learn the secret of time travel if you heard it from yourself in the future? Can you become your own mother, daughter, and grandmother simultaneously, as in Robert Heinlein's story? It seems only a theory of everything can sort this out. So all these mysteries of black holes, wormholes, and time travel will probably remain unsolved until we understand how quantum effects affect gravity and space-time itself. Only then will we know what awaits the stationarity and immutability of the universe. But his own equations led to the opposite result. The universe simply refused to be static. To ensure the stationarity of this world, it was necessary to introduce the famous cosmological constant, lambda, into the equation. This is a kind of mathematical plug that was supposed to balance universal gravitation and prevent the universe from collapsing under its own weight, as the formulas demanded. The physical meaning and nature of this anti-gravity remained a mystery. But since galaxies hang motionless in space, something must counteract their attraction to each other, Einstein reasoned. Another feature of his model was the finiteness of the universe. What does that mean? What happens if you get into a spaceship with infinite fuel and travel to the edge of the universe? Will you hit a wall with the inscription, "End of the world"? No. Space itself is curved and closed in on itself, like the surface of a sphere. Flying straight all the time, we will eventually return to the starting point from the other side. There are no edges here, and although our world is huge, it has a very specific volume. This is much like how the surface area of the Earth is finite, although it has no mathematician Alexander Friedman. Analyzing the equations of relativity, he came to a sensational conclusion. They describe not only a static universe, but also non-stationary models of an expanding or contracting universe. In 1922, Friedman showed that 3 scenarios for the evolution of the universe are possible depending on the average density of matter. If the density is greater than critical, then expansion will eventually be replaced by contraction. Galaxies will fly apart more and more slowly, as if connected by rubber bands. Then they will stop and, under the influence of gravity, begin to approach each other with acceleration until they merge into a single point, a kind of Big Bang in reverse. At critical density, expansion will continue forever, but with deceleration. Galaxies fly apart by inertia, gradually weakening mutual attractions. And if the average density is less than critical, then the universe expands indefinitely, with continuous acceleration. In any case, the universe turns out to be non-stationary. The distances between galaxies do not remain constant. In other words, the cosmos was not always as it is now. 2 explanations for the vast dispersion of galaxies suggested themselves. Either these stellar islands somehow immediately arose at colossal distances and are now slowly converging under the action of gravity, meaning in the future they will merge. Or, conversely, initially, galaxies were much closer, or even at a single point, and then an unknown force scattered them across space. But in both cases, the universe clearly had a beginning. There was a moment zero when something grandiose happened. Either galaxies suddenly appeared already separated by enormous distances, or they were born in one place, and then a powerful impulse scattered them in different directions like billiard balls after a cue strike. Thus, for the first time at a scientific level, the question of the beginning of the world was posed, and immediately the first spoilers appeared, revealing the main intrigue of the universe. But as with any spoilers, many preferred to wait for official confirmation for the dark night sky. Light from distant galaxies simply hasn't had time to reach us. As for gravity, its influence is limited either by the finite mass of the universe or by the high speeds at which galaxies are receding. They simply overcome gravity. Naturally, this theory generated a host of new questions. What preceded the emergence of the universe? Why did the Big Bang happen? How does the monstrous compression of countless galaxies into a point occur? And isn't the very fact of the universe's birth an act of its creation by someone from outside? Friedman did not know the answers to these profound philosophical questions. Einstein did not accept his idea, although he acknowledged the mathematical correctness of his colleagues' empirical verification was required. Yes, experiments with entire galaxies are impossible under terrestrial conditions, but one could try to measure their speed of movement using the Doppler effect, that is, by the shift of spectral lines towards the red side for recession or the blue side for approach. In 1927, in the mountains of California, Edwin Hubble began his work, equipped with the most powerful 2.5-meter reflector telescope of the time and a modern spectrograph. This instrumentation allowed him to capture the faint light of distant galaxies and analyze their spectra for Doppler shifts. Hubble expected to get a chaotic picture of movements. Some galaxies should have been approaching us, some receding, but it was not to be. It turned out that the nearest galaxy, Andromeda, is indeed moving towards us at a speed of about 100 kilometers per second, but all other galaxies had redshifts indicating their recession from the Milky Way. Moreover, a clear dependence was observed. The farther the galaxy, the faster it flies away from us. This was called Hubble's law. The conclusion was unequivocal. The universe is non-stationary. The mechanism of expansion. Imagine that galaxies are points drawn on the surface of a balloon. As the balloon inflates, the points move away from each other. Moreover, the farther apart they were initially, the faster the distance between them grows. Regardless of which point we choose as a starting point, the picture will be the same. And could scientists then determine the moment when all galaxies were very close, that is, literally at one point? Yes. Hubble's law made it possible to estimate the age of the universe, that is, the time elapsed from moment zero to our days, and this age turned out to be in the range of 13.7 to 13.9 billion years. Imagine almost 14 billion candles on the universe's birthday cake. It is pointless to look for the point where all matter was gathered at moment zero. It is any point in the universe. Therefore, the inhabitants of any galaxy have the right to consider themselves the center of the world. Both Nicholas of Cusa and Giordano Bruno were right. In your opinion, there was nothing, and suddenly there was a big bang, and from nothing, from a point, the entire universe arose. How can this be? If ancient thinkers wondered about the elements that make up the world, then in the 20th century, the chemical composition of cosmic bodies became known. Analysis of star spectra showed that they consist of two simplest elements, hydrogen, 75% of the mass, and helium, 25%. And all other heavy elements make up only about 1% of stellar matter. This ratio turned out to be typical for the interstellar medium as well. Why is there 3 times more hydrogen in the universe than helium? Where did this proportion come from at all? German physicist Hans Bethe delved deeper and discovered nuclear reactions in the cores of stars, in which one helium-4 nucleus is formed from 12 protons of hydrogen nuclei. That is, if all cosmic helium arose from hydrogen, then its mass should be 3 times less. But there is a nuance. The speed of these reactions in stars is too slow. Over the lifetime of stars, which is 5 to 10 billion years, thermonuclear synthesis simply does not have time to significantly change the initial composition of matter. It seems stars were formed already from a mixture in which helium developed by George Gamow, a former student of Friedmann. Comparing the composition of the universe and models of its expansion, Gamow realized that in the first moments after the Big Bang, the density and temperature of cosmic matter were so high that part of the hydrogen had already managed to turn into helium. At the same time, elements heavier than helium did not arise. The conditions were still unsuitable for them. Thus, the theory of the primary synthesis of elements in the universe was developed by Gamow and his graduate student Ralph Alpher. By the way, Gamow added Hans Bethe as a co-author after writing the article, just so the theory would be called alpha, beta, relying on the laws of thermodynamics, understood that at such a high initial temperature, matter must have been in complete thermal equilibrium with radiation. Calculations showed that in this primary broth of hydrogen and helium, there should also have been photons, and with a huge preponderance, there should have been billions of orders of magnitude more of them than atoms. That is why heavy nuclei could not form. However, as the universe expanded, the energy density of radiation fell faster than the mass density of matter. Gradually, the role of radiation in the dynamics of the universe became secondary. But where did these relic photons go then? Gamow and his colleagues proved. Nowhere. Simply because of the expansion of the universe, the wavelength of primary photons continuously grew. If in the first moment after the Big Bang they were high-energy gamma quanta, then after billions of years of expansion, they turned into microwave radiation. Even today, we should be literally immersed in this thermal radio background, uniformly filling the cosmos. According to calculations, the temperature of this radiation should be in the range of 0 to 10 degrees Kelvin. So, theorists predicted what to look for. Alas, at first, the scientific community simply did not notice. As often happens in the history of science, a brilliant hypothesis, radio astronomers from the Pulkovo Observatory did indeed register a microwave background of the required spectrum, but they did not realize the significance of their discovery. And a little later, the unforeseen happened. Employees of Bell Laboratories, Arno Penzias and Robert Wilson, while debugging receiving equipment for satellite communications, encountered a strange microwave noise. It did not depend in any way on the direction of the antenna or the time of day. In an attempt to get rid of it, engineers cooled the detectors with liquid helium and even cleaned out white dielectric material from under a pigeon's nest built in the antenna. All was in vain. The mysterious background stubbornly poured from all over the sky. Imagine Penzias and Wilson turned out to be the discoverers of relic radiation without suspecting it themselves, and in 1978 they received the Nobel Prize. The background generated by the Big Bang really exists. Its characteristics exactly match the predictions of Gamow's hot universe theory. It uniformly fills the entire cosmos, which confirms the homogeneity and isotropy of the universe even in the first moments of its life. After all, the microwave background itself arose only 1/10,000th of a second after the Big Bang, and began to propagate freely after 380,000 years, when the plasma of the universe cooled and became transparent. The discovery of relic radiation became the second direct confirmation of the Big Bang concept after Hubble's law. No alternative theories from the Earth's atmosphere, receivers for registering the relic radiation began to be placed on satellites. The first such experiment was the Soviet Relikt 1 complex. It took place in 1983 on the Prognoz 9 satellite, but its sensitivity was not enough to discern the fine structure of the radiation. A breakthrough was made by the American COBE satellite in 1989. It turned out that the relic background is not perfectly uniform. It has tiny fluctuations in temperature and intensity. It turned out that the young universe was not completely smooth. It contained minute inhomogeneities in density and temperature. It would seem all logical. Weak density perturbations in the young universe should have been amplified by gravity and generated matter clumps. After all, in regions with higher density, gravity begins to attract matter more actively. This leads to an even greater increase in density. A self-sustaining process of gravitational instability is launched. The initial fluctuation, like a snowball, gathers surrounding matter onto itself. This is how protogalaxies are born, and within them, individual clumps, protostars, and those under the influence of their own weight, heat up and ignite with thermonuclear flame. This idea seems logical, but when scientists try to describe it using mathematics and physics, was that the universe is constantly expanding, and because of this, the density of matter in it decreases. This expansion prevents matter from gathering into denser regions. It's unclear how small clumps of matter could overcome the expansion of the universe and form galaxies. The second problem is related to the fact that the early universe was very hot and dense. Because of this, particles of light, photons, constantly collided with particles of matter, electrons, preventing clumps of matter from growing. Only when the universe cooled sufficiently and electrons combined with protons into atoms did matter become transparent to light and clumps could grow. But calculations show that the clumps that could have formed then do not match what we see in the relic radiation, the echo of the early universe. It turns out that ordinary matter made of protons and electrons cannot explain the observed structure of the universe. Came from an unexpected direction. It turned out that besides ordinary matter, the universe is filled with a completely different substance. Dark matter. Its existence was independently inferred from anomalies in the rotation of galaxies. Astronomers had long noticed that spiral galaxies rotate somewhat incorrectly. Stars on their outskirts move just as fast as those in the center, resembling the rotation of a wheel. To explain this, it had to be assumed that the visible matter of galaxies is located within invisible matter, the mass of which is 5 to 6 times greater than the total mass of all stars and gas. It turned out that galaxies are like icebergs. Only a small part of them is visible, while the lion's share of the mass is hidden from view, manifesting itself only gravitationally. This mysterious substance was called dark matter. But what is it? The option of invisible objects made of ordinary matter was quickly dismissed. Their mass is insufficient. It is much more natural to assume that dark matter is some new type of fundamental particle. Apparently, they participate only in gravitational interaction, but know neither strong nuclear nor electromagnetic forces. Therefore, these particles cannot form atoms and do not interact with radiation. They freely penetrate ordinary matter. Right now, dark matter is passing through your body. Creepy, right? Physicists have already come up with a general name for these particles. WIMPs, weakly interacting massive particles. The main candidate for the role of WIMPs for a long time was considered to be hypothetical supersymmetric partners of ordinary particles, neutralinos. Alas, their traces have not yet been found at the Large Hadron Collider. Now, the main hopes are pinned on other options, axions, sterile neutrinos, and Jim Peebles realized the cosmological role of dark matter. The temperature of the relic radiation reflects the distribution of ordinary baryonic matter in the young universe, but not WIMPs. The latter had already begun to gather together under the action of their own gravity, and when baryons cooled and became transparent to radiation, they simply fell into the prepared gravitational wells of dark matter. Thus, clumps of dark matter were able to develop unimpeded, becoming the seeds of future galaxies. Eventually, visible matter settled into the potential wells of these seeds. Computer modeling of the universe's evolution, taking dark matter into account, yielded stunning results. Theoretical calculations perfectly matched the data from the Planck probe. Moreover, the calculations reproduced the cellular structure of today's cosmos. Superclusters of galaxies form, as it were, the walls of bubbles, and inside these bubbles there is almost nothing. We have truly understood how today's cosmic structures arose from the homogeneous early universe. Now all that remains is a small matter, to catch dark matter particles in experiments. This will allow us to establish the specific physical nature of the elusive WIMPs, although it cannot be ruled out that dark matter will turn out to be something completely different. We have finally grasped the secrets of the universe. Most scientists were forced to admit the non-stationarity of our universe. Some met this with hostility, others with enthusiasm. There are still people who deny the Big Bang and consider it a ridiculous invention of scientists. Heck, some commenters still believe the Earth is flat, but even the most ardent supporters of the Big Bang Theory admit that it has serious problems. The main one is the horizon problem. Let me remind you that the relic background is striking in its homogeneity. Its temperature in all directions coincides with an accuracy of hundredths of a percent, and the tiny fluctuations are also the same everywhere. Imagine that we pointed a radio telescope at section of the sky A, and then at section B in the opposite direction. Why are the relic signals from A and B so similar? After all, the distance between these regions today is about 90 billion light-years. That is, A and B could not have conspired and influenced each other in any way. Since the Big Bang, light has only had time to travel 13.8 billion light-years. That is, only points no more than this distance apart can be somehow connected. This limit is called the horizon. How then to explain this amazing consistency of the relic background in all directions? Even if A and B were much closer in the past, a signal between them still would not have had time to propagate. A and B were never causally connected. But why do the conditions in them coincide with incredible accuracy?
Another problem
What is responsible for flat geometry of the universe? According to Friedman's models, the future fate of the world depends on the average density of matter. If it is greater than a certain critical value, gravity will sooner or later stop the expansion and force the universe to contract back into a point. If the density is below this mark, the expansion will be eternal. But the Big Bang could have produced any amount of matter and radiation. Why did the average density of the cosmos turn out to be so close precisely to the critical value? The chances of coincidence are negligible. At critical density, the universe has zero curvature and unlimited volume. This is flat geometry. What kind of perfectionist so carefully adjusted the initial conditions so that after billions of years, the density would be close to critical with an accuracy of 15 the universe expanded not by inertia, but with acceleration? This would solve the horizon problem. Then an initially causally connected region could have flown apart so quickly that its fragments lost the ability to exchange signals. But what could provide such accelerated expansion? A hint came from Einstein. Remember, he introduced the cosmological constant into the equation, the very anti-gravity, to make the cosmos static. Einstein himself called this his greatest mistake. But subsequently, scientists wondered if something similar really existed, and if this force outweighed the usual attraction of masses, then the universe would expand with acceleration. Curiously, as early as 1917, astronomer Willem de Sitter considered a model of an empty universe containing only the cosmological constant, and showed that in such a world, two bodies would accelerate away from each other, and the acceleration would be faster the greater the distance between the bodies. It turns out this force does not weaken with distance, but rather increases. Isn't this the key to the mystery of the accelerated expansion of the early universe? However, neither Einstein nor de Sitter could say what exactly creates anti-gravity. It turned out that this is simply a property of the very space of the universe. But then we again have to reconsider the notion of space as something filled with fields. Any point, even an empty one, can attract or repel particles placed in it. This means fields, and with them space, contain energy. What used to be called emptiness, physicists call a vacuum. But this is by no means a synonym for nothing. A vacuum is an active medium permeated by energy-intensive fields, and perhaps it is the energy of these fields that provides the anti-gravity, causing the accelerated inflation is this. Immediately after its birth, the universe experienced a brief period of very rapid, exponential expansion. This initial phase of inflation lasted a negligible fraction of a second, but during this time, a tiny region of space measuring 10 to the power of minus 27 centimeters increased by 27 orders of magnitude, reaching a diameter of about 1 centimeter. According to the inflation hypothesis proposed first by Alexei Starobinsky and then developed by Alan Guth, the cause was an exotic state of matter, that is, a high-energy vacuum. Unlike our usual vacuum, this initial vacuum possessed a colossal energy density. Each cubic centimeter of it weighed as much as the moon. Such a supervacuum generates enormous negative pressure. Anti-gravity, 3 times greater than the usual gravity of matter. Under the influence of this anti-gravity, any lump of high-energy vacuum will begin to expand rapidly. Every 10 to the power of minus 38 seconds, its dimensions will double. This is what happened to the progenitor of our universe. Okay, but why then did this hyperinflation stop and give way to normal expansion? Physicists believe that the initial vacuum is unstable. It inevitably decays, transitioning to a normal state with low energy density. According to Einstein's formula, E equals mc squared, the excess energy transforms into the mass of elementary particles. Quarks, leptons, photons, etc. The high-energy vacuum, as it were, evaporated, giving rise to the familiar matter and radiation of the early universe. It is this decay that is perceived as the Big Bang. In a gigantic flash, almost all the contents of our world were born. Nuclear particles, electrons, neutrinos, quanta of light. This put an end to anti-gravity. The high-energy vacuum was no more. Therefore, after the Big Bang, expansion slowed down, obeying the usual gravity of the newly born particles. However, the enormous inertia of inflation did not disappear, and expansion continued, albeit at a slower rate. Solves the puzzles mentioned earlier. The horizon problem, that is, the homogeneity of the universe, is resolved simply because in the inflationary scenario, different regions of our universe indeed had a common past. They were close together, inside a tiny bubble, and only then were they carried apart to gigantic distances. The same applies to the problem of the flatness of space. Inflation was so powerful and rapid that we simply do not notice the global curvature of the world, just as an ant does not feel that it is crawling. To measure the distance to nearby galaxies, Hubble used the method of standard candles, that is, objects of known luminosity, called Cepheids. But how to determine the distance to distant galaxies, which are visible even in the best telescopes only as faint specks? New beacons were needed, and in 1977, astronomer Yuri Pskovsky proposed using type Ia supernovae for this. They arise from the thermonuclear explosion of a white dwarf. Perhaps this is the most dramatic way to declare one's existence. The luminosity of a supernova is comparable to the glow of billions of stars in a galaxy. They are rare, but in the gigantic volume of the visible universe, they flare up quite often. In 1998, Brian Schmidt and Adam Rees published stunning data on 16 supernovae. It turned out that their brightness was lower than expected for the measured redshift. This means that these galaxies are farther away and receding faster than Hubble's law predicts. The acceleration graph clearly curved upwards. A year later, Saul Perlmutter's group confirmed this result with 42 supernovae. Something was clearly accelerating the galaxies, causing them to fly apart with increasing speed. A repulsive force, anti-gravity, is acting in the universe, increasing with distance. In 2011, Perlmutter, Schmidt, and Rees received the Nobel Prize to change the understanding of the world. If before the debate was only about whether there was enough gravity to stop the expansion and collapse of the universe, now it became clear. Expansion will be eternal due to the dominance of anti-gravity. Galaxies will continue to fly apart, losing the ability to see each other. So what causes this acceleration? This unknown force was called dark energy. The first hypotheses about its nature used developments from inflationary theory. Remember how after the Big Bang, the superenergetic vacuum turned into an ordinary vacuum with zero or negligible energy density? Well, the acceleration and expansion hint that the energy density there is still higher. Apparently this is dark energy, or Einstein's cosmological constant. In this model, it uniformly fills the entire universe and intergalactic space and is not diluted. Its density is constant in space and time. It does not interact with matter. Calculations showed that about 7 billion years ago, the average density of matter fell below the density of the vacuum, and since then, the universe has been expanding gives the following composition of the universe. Dark energy around 70%, dark matter 26%, and all other baryonic matter, i.e., ordinary matter, only 5%. Astonishing. Astronomers have studied only 0.5% of the universe's mass for 2,500 years. But what exactly are dark matter and dark energy, which make up most of our world? Strictly speaking, we do not yet know. But right now, scientists are working on hypotheses that will probably soon shed light on this as well. We are lucky to live in a unique era when the universe has already cooled enough for complex structures to appear, but has not yet had time to fly apart so much that galaxies lose sight of each other. Expansion will continue forever, accelerating to the limit set by the density of dark energy. Galaxies will recede until they turn into unreachable islands of light. The last stars will burn out, and the cosmos will plunge into twilight, illuminated only by rare supernova flashes. And after unimaginable quintillions of years, even black holes will evaporate and turn black, leaving only cold emptiness in the universe. Brrr. Of course, this is still just a scientific model, not firmly established facts, but this is precisely the picture that modern cosmology, the fruit of centuries of labor and insights of thousands of scientists, paints for us. And who knows, maybe our minds appeared just in time to By looking into the abyss of the future, find a super dense vacuum that gave birth to our universe come from? Maybe it arose in the depths of some other world, and does that maternal reality exist now? What if right now in our cosmos the embryos of new universes are being born? The honest answer for now is one. We do not know, but science has some ideas. For physicists, the mechanism for the appearance of clumps of high-energy vacuum does not look overwhelmingly complex. If we could look into the microworld with a magnification of 1 billion times, we would see how virtual particles, ghostly portions of matter, are born and immediately disappear at every point in space. It's like the motivation to exercise every morning. Usually these particles annihilate almost instantly, emitting quanta of light, but if a sufficiently powerful field is nearby, it can separate these particles before they disappear. Then they will become quite real, as if arising from nothing, although in essence the energy of the external field will create them. In the quantum foam, all sorts of particles constantly arise, including those corresponding to an unstable vacuum. One fluctuation is enough for the expanding tension of the vacuum to unfurl a pocket of spacetime hidden within it into an entire universe. Such an event is unlikely, but not impossible. But where does so much energy come from in a tiny particle to turn into the mass of the Big Bang? For clarity, let's recall black holes. From the outside, they look compact, but inside they hide a monstrous supply of mass energy. Gravity once gathered and compacted a huge amount of matter into an extremely small volume, pumping colossal energy into it. It is enough to curve and tear the fabric of spacetime at this point. It turns out that even if an object seems tiny from the outside, the special geometry of its internal spacetime is capable of accommodating an entire universe with enormous energy content. Perhaps our cosmos is just the interior of a black hole in an unknown external world. This is not excluded, although not proven. In principle, a supermassive particle called a Friedmann can also hide an endless universe within itself. To an external observer, such an object will look like a negligible fluctuation, although by its own clock, it can live now microworlds are constantly being born in our universe. Paradoxically, this is possible. You might think this is nonsense, but physicists treat this absolutely seriously. One of the options for the origin of universes was proposed in 1983 by physicist Andre Linde. According to his theory, a rapidly expanding parent universe continuously generates similar microworlds, and the distance between them immediately increases. As a result, an innumerable family of worlds arises, each of which can also fragment during its own accelerated expansion. In such a model, there can be countless universes. Then our cosmos is just one of the bubbles in the giant foam of the multiverse. The idea of the multiverse explains how it happened that life was able to originate in our universe at all. After all, if we go through all conceivable variants of fundamental properties, from particle masses to world constants, it turns out that almost all of them are incompatible with our existence. The slightest deviation of these parameters from their current values and the universe would become lifeless, even without atoms, stars, and planets. It seems as if someone specially adjusted the cosmos for future observers. One can imagine a higher civilization that configured our universe by launching inflation from a correctly formed vacuum clot. It is possible that someday Earthlings will also learn to program microworlds through controlled matter collapse. There is another explanation. After all, if the multiverse generates all possible combinations of fundamental properties, then among this diversity, unlikely variants such as our world will inevitably be found. Somewhere, a random fluctuation will necessarily produce a set of physical parameters ideally suited for the emergence of complex structures, stars, planets, galaxies, life, and reason. Therefore, there is nothing surprising that our universe is so friendly. If it were different, we would not be here, and there would be no one to be surprised. The multiverse truly boggles the imagination. There's a possibility that somewhere out there, an immortal version of me exists. In our universe, I am still working on that. However, not all scientists share the concept of the multiverse. Any sound hypothesis should offer a way to test it experimentally, but parallel universes by definition cannot affect ours. Therefore, their existence is fundamentally unprovable. No thought experiment or real experiment can detect neighboring worlds, so is it worth talking about them seriously at all? On the other hand, in recent years, scientists have increasingly encountered hypothetical objects that do not directly contradict physical laws but are inaccessible to experiments. We seriously discuss dark matter, primordial black holes, or wormholes. In essence, these are also entities beyond direct verification, at least for now. Ideas about the multiverse and multidimensional spacetime should be perceived at least as powerful computers are calculating the most complex models. Telescopes tirelessly catch signals from the sky. Accelerators and colliders penetrate the depths of the microworld. Scientists compare their hypotheses with measurement results, striving to find the truth. Step by step, science is approaching an understanding of the fundamental foundations of the universe, and yet skeptics do not relent. How? Scientists still know almost nothing about elementary things. What caused the Big Bang and what was before it? What are the mysterious dark matter and energy made of? How many parallel universes are there in total? Should I take an umbrella? Yes. While our knowledge is not perfect and not complete, it is growing. Since the era of Giordano Bruno, the volume of accumulated knowledge has grown by orders of magnitude. We are already discussing hypotheses trying to explain dark energy and dark matter. We have proposed the idea of a multiverse. We are discussing the paradoxes of the anthropic principle, but these are still only hypotheses. Further research, if not tomorrow, then in 400 years, will provide answers to these and other, perhaps not yet posed, astonishing questions. Science will find answers to them. The pace of scientific progress is accelerating. It is difficult to even imagine what discoveries await our descendants in the coming centuries. They will look at the ideas of the 21st century in the same way we look at the conjectures of the Middle Ages. Fortunately, it is important to consider that much of what is discussed here are reasoned hypotheses that may or may not be confirmed. Indeed, all of science is built upon this foundation. There is a notion that certain topics, when contemplated deeply enough, can quite literally drive a person to madness. Perhaps you've sensed this when exploring similar ideas, assuming, of course, a certain level of impressionability. It is possible that today we will delve into the abyss of potential madness more profoundly than ever before. Many have heard that the age of our universe is approximately 13,800,000,000 years, and that it originated from a Big Bang. But the question here is what we call the universe and what beginning signifies. When you hear the phrase, the universe appeared from nothing, it likely means not from absolute nothingness, but from something we do not yet know how to describe. Furthermore, theoretical physicist Matt Strassler, in his article, The Hot Big Bang, writes that when we speak of the age of the universe, we are only referring to the period from the beginning of the Big Bang to the present day, but this does not mean that nothing existed before the Big Bang, and a similar principle applies not only to time, but also to space itself. It is suggested that the universe was concentrated into an infinitely small point at the moment of the Big Bang and supposedly had a finite size, perhaps smaller than a single atom, or so it is often said in popular science. However, this refers only to the observable part of the universe. Thus, it does not at all mean that the universe was not infinite at the moment of the Big Bang. In fact, all data suggests that the universe is indeed infinite, which means it was much denser but still just as infinite at its very beginning. And infinity is one of those things you probably shouldn't think about too much. Soon, everything said will become a little clearer. In August of 1881, Nietzsche was strolling along Lake Silvaplana, near the village of Sils Maria in Switzerland, and stopped to rest right by a particular pyramidal rock. At that very moment, the philosopher was struck by an insight so powerful it nearly crushed him, as he would later express in a letter to his friend and assistant Peter Gast. "On my horizon has risen a thought, the like of which I have never known." This moment was so significant that it was immortalized with a plaque on the rock, the quote on which literally states, "I stopped by a mighty pyramidal block not far from Surlade. It was then that this thought came to me." Nietzsche realized that the idea that had struck him should become the most central in his philosophical teaching, but at the same time the most terrible. So terrible that he spoke of it with great reluctance. Many who knew him well, particularly his friend Franz Overbeck and his unrequited love Lou Salome, later reported that Nietzsche spoke of this idea in a whisper, implying it was some unheard-of discovery. According to Nietzsche, this thought would not be crushing, given proper reflection, only and exclusively for the so-called Übermensch or Overman. The Overman is not some comic book character, but an image introduced by Friedrich Nietzsche to denote a being who, by its power, should surpass modern man to the same extent that the latter has surpassed the ape. And speaking of power, it refers more to psychological qualities. We will get to the very thought that illuminated Nietzsche, but first, much needs to be explained. Let's start with one of the most astounding cosmological oddities known. You are aware, are you not, that the farther an object is from us, the smaller it appears? For example, from a bird's eye view, people look like ants. The same occurs in the nearer parts of cosmos. The sun is 400 times larger than the moon, but during a total solar eclipse, the moon almost perfectly covers it because it is 400 times closer to us than our star. And this entire pattern of changing sizes depending on distance persists over billions of light years. That is, the farther a galaxy, the smaller it appears to us, as one would expect. However, at a certain point, at a distance of approximately 14 billion light years, an entirely opposite pattern suddenly begins to operate. Namely, the farther an object, the larger it seems. And there's a simple, yet profoundly somber explanation for this. To begin with, though it is hard to believe, by looking at any star or galaxy in the night sky, you are at that very moment experiencing the gravity. However, believe it, the force of gravity would be sufficient for all massive objects in our universe to eventually collapse. You could never move far enough from an object to not experience its gravitational influence at some level. Meanwhile, our universe is not collapsing. In fact, something quite the opposite is happening. We do not know why, but the universe is expanding, and it is doing so with acceleration. And since physicists have no idea what causes the universe to expand, they usually call any hypothetical phenomenon capable of accelerating the universe's expansion dark energy. Yes, I know you are probably tired of hearing about dark energy in every other discussion about space, but friends, dark energy is, by all appearances, one of the most repugnant phenomena that exist. So do not dismiss it prematurely. Catherine Mack, an assistant professor of physics at North Carolina State University, writes, "If you ask my colleagues, they will say they strive to understand the nature of dark energy, because it can tell us a lot about fundamental physics and our cosmological model. But I know that what actually drives them is fear." So, the expansion of the universe, rewinding time by 13.8 billion years to somewhere near the very, very conventional beginning, we find a paradoxical moment in which, for reasons not entirely clear to us, the expansion of the universe suddenly accelerated, and the region that was to become our observable universe increased in size by more than 100 trillion times. This happened much faster than the speed of light, because there are no restrictions on the speed of expansion of space itself. I understand that our brains are not equipped to imagine such numbers, but for some clarity, here is what theoretical physicist Matt Strassler, mentioned earlier, writes. How insane were the rates of expansion? A section of the universe no larger than your computer screen expanded to the size of the observable universe, or larger in less time than it takes a quark to cross from one side of a proton to the other. But then this monstrous expansion, again for unknown reasons, slowed down, and this past frenzy is called the cosmic inflation hypothesis. We do not know for sure if that initial expansion is related to the expansion we observe now. But importantly, we currently have no reason to believe that cosmic inflation cannot happen again. For instance, right now, as you consider this, we wouldn't even have time to understand anything. If such a thing were to happen, it would be terrible. Yet the simple disappearance of humanity would not be the worst possible outcome. You might ask, what could be worse for humanity than the demise of all humanity? So, we continue. The universe experienced a stage of inflation after which expansion slowed. But about 6 billion years ago, expansion began to accelerate again. We know this thanks to the processing of vast amounts of data, including by complex modern computer programs. You have surely heard that the universe expands not from a specific point, but at all points simultaneously, and therefore, the farther an object is, the faster it recedes from us. If this isn't clear, here's a simple example. When stretching a child's toy spring, each coil moves away from its neighbor by only the width of a finger. Yet two coils at opposite ends of the spring move apart by more than a meter. Now imagine the spring is infinite. The same applies to galaxies in the universe. Thanks to this mechanism, distant galaxies can recede from us at the speed of light, or even faster, because as a reminder, no prohibitions apply to the speed of space expansion, and it is precisely the expansion of space that is the reason why, at a certain distance from us, objects begin to appear larger the farther away they are. This occurs for the same reason we can observe objects that are currently receding from us at superluminal speeds due to the expansion of space. At the time when these, in quotes, superluminal objects emitted their light, they were much closer and occupied more space in the sky because the universe itself was denser. Despite being much farther now, the snapshot they sent us traveled all this time, and because the universe's expansion rate slowed for a period, as you recall, this snapshot has now reached us, showing a ghostly image of a much closer and much more ancient object. Thus, the farther back in time we look, the more compact a universe we observe. Therefore, a galaxy that is now farther than another galaxy might have been closer at the moment it emitted light. Hence, the paradox of perception arises. You have probably been waiting. Here's a real example. One of the most distant galaxies we have ever observed is GNZ 11. The ghostly snapshot we see traveled to us for approximately 13.5 billion years. So it seems to us that GNZ 11 is much closer, but it is not. Looking at GNZ 11, we are, in a way, looking not at today's universe, but at the universe as it was just 400 million years after the Big Bang. Let me remind you, it was much more compact then. Meanwhile, due to the expansion of the universe, GNZ 11 is currently about 32 billion light-years away from us, and it actually appears twice as large as a galaxy of the same size that is twice as close. A paradox of perception. You know that a light-year is the distance light travels in a year, And it would seem that since the universe is 13.8 billion years old since the Big Bang, we should be able to see a maximum of 13.8 billion light years. But in reality, due to dark energy, we see much farther, which is also no secret to many of you. Today, the farthest distance we can see is a sphere with a radius of 46 billion light years. And this is only for now. In the future, this sphere will continue to grow due to the expansion of space, but only up to a certain limit. By performing some calculations, we can determine the future limit of visibility. It will be approximately 33% larger than the current one, namely 61 billion light years from us. But gradually, the image of galaxy GNZ 11 will dim and disappear forever, because as you understand, the light that this galaxy is emitting now will never reach us, unless of course the expansion slows down again. And at this moment, galaxy GNZ 11 is receding from us at a speed of 687,000 kilometers per second, more than twice the speed of light. And this is sad, but even sadder is that it doesn't end with GNZ 11. Think about it. More than 96.7% of the galaxies we can observe today have already disappeared by the same principle. 98.6% of the galaxies we will ever observe have already disappeared. In other words, in the future, we are set to see a total of 4.7 trillion galaxies, and 4.634 trillion of them are already forever beyond our reach, even if we could travel towards them at the speed of light. And only about 66 billion galaxies are still accessible to us today, I emphasize, today, because this is a problem that will worsen over time. Right now, if we assume that each of the 66 billion galaxies has as many stars as the Milky Way, about 400 billion, this means that there are approximately 60,000 stars disappearing from our field of view with every passing second. This is about 50 million stars in the time you've been considering this information. We will still be able to see their former light for billions of years, but any new light they create from this very moment will never reach us again. We are no longer causally connected to these objects. Regardless of what we do from this moment on, we will never be able to influence them, nor will they be able to influence us. Any information about these places is now fundamentally inaccessible to us. Even with arbitrarily advanced technologies, more than 98% of all galaxies we will ever see are already beyond our reach. If the force of space expansion can never overcome the gravitational force within galaxies, then gradually each galaxy or local group of galaxies will slowly sink into darkness, left in complete solitude. Gradually existing stars will burn out, particles will decay, black holes will evaporate thanks to Hawking radiation, and the universe will become merely empty space containing only dark energy, ensuring exponential expansion for eternity. Here it should be noted that dark energy is a kind of opposite to gravity. That is, the more filled space is, the stronger the force of gravity, and the emptier space is, the stronger dark energy becomes because, although it is counterintuitive, its density per square meter does not decrease with the expansion of space. So do you understand what is happening? As the process of the universe's expansion accelerates, there will be more and more empty space, which in turn will lead to an acceleration of the expansion process, which will lead to an increase in empty space, and so on ad infinitum. Events in some parts of the universe will not be able to influence events in others. Eventually, the universe will be empty space with only dark energy ensuring its exponential expansion. This is called de Sitter space, and according to physicists, it evolves much like the very early cosmos during the inflationary stage. But unlike inflation, this expansion will last forever. Can such infinite expansion be considered the end of the universe? The question here is what we call the universe and what end means. You see, if we consider, for example, the concept of time, it turns out to be one of the unresolved mysteries of physics. No one knows why it should flow in a particular direction. Consider particles in motion. Are they moving into the future or into the past? You don't know the answer because regardless of which way an animation of them might play, the laws by which these particles move would remain the same. It is believed that physical processes at the microscopic level are either completely or mostly symmetrical in time. If the direction of time were reversed, changing the direction of time in the equations would not affect the result in any way. The theoretical statements describing them would remain true. Now observe something else. Is paint separating from water or mixing with it? Here you definitely know where the past is and where the future is, because at the macroscopic level, there's an obvious direction of time. Thus it seems the only part of physics that cares about the direction of time is entropy. Why does your closet full of clothes become a complete mess again sometime after cleaning? Imagine your closet, and imagine all the possible ways to arrange things in it neatly. Excellent. Now imagine all the possible ways to arrange them messily. And because there are many, many more messy arrangements, the probability that the system called closet with clothes will gradually become more and more chaotic is higher than the probability that this system will continue to maintain some ordered form. because of the second law of thermodynamics, which states that in an isolated system, the total entropy cannot decrease, your closet sooner or later returns to a state of disarray. You might say, well, I folded the clothes, thereby reducing the entropy inside the closet. Did I violate the laws of physics? No, because the closet is not an isolated system, and you expended a lot of energy cleaning up. You digested food and exhaled carbon dioxide. The air in the room heated up through convection and sweat, so the total entropy increased even more. By the way, this is precisely why if you want to cool a room by leaving the refrigerator door open, the room will eventually not cool down, but heat up. And I remember being puzzled when it was said that air conditioners contribute to global warming. Every attempt we make to order some part of the world creates disorder in another part, usually in the form of heat. And we certainly don't know this for sure yet, but perhaps it is entropy that creates what we call time. Everything you see now, galaxies, stars, people, is all the result of the fact that, for some reason, the universe at the moment of the Big Bang was in an improbably ordered state. And the gradual movement from that initially ordered state of the universe to a disordered state is what we call the passage of time, like mixing paint in water. And just as we could not determine which way time flows in frames of paint already completely mixed in water, in exactly the same way, in a universe that has reached maximum entropy, the concept of the arrow of time ceases to exist. The fact that you feel the arrow of time is directed in one and the same direction, in other words, that very flow of time, indicates that the universe has not yet reached the equilibrium state towards which it strives according to the law of entropy. But having reached the de Sitter state, the universe will have maximum entropy, because from that moment on, the total entropy of the universe can no longer increase. This means that nothing more can happen in the usual sense, because for something to happen, energy must move from one place to another. But alas, the paint in the water has completely mixed. Yes, in a sense, a synonym for the word entropy is homogeneity. Given that the universe expands not from a single point but at all points simultaneously, when it reaches the stage of exponential expansion around any point, a sphere can be drawn, beyond the boundary of which will be a forever hidden part of the cosmos, just as those stars I spoke of are now forever hidden from us. And this has a name, the heat death of the universe. You might ask, what does this have to do with us? Why did I say this is worse than the demise of humanity? By the time of the heat death, we will have been gone for so long that it makes no difference. And here we come to what was mentioned at the beginning, because there is one nuance that changes everything. Ask yourself two questions. First, what happens when you have an infinite amount of time? And second, what happens when you have an infinite amount of space? The answer to both these questions is everything, literally everything within the laws of physics. Could I suffocate because all the oxygen in my room gathers in that far corner? Never. Entropy protects me from this situation because, as you remember, there are many more disordered states than ordered ones. Therefore, such a version of my demise would not even cross an investigator's mind. But in reality, when we say the word never, we often mean usually. A decrease in disorder in a system is possible. It is just extremely, unimaginably improbable. Usually people do not suffocate because all the oxygen gathers in one corner of a room. But hypothetically, if I were to sit here for an infinite amount of time, it would happen with 100% probability. With 100% probability. And a completely empty universe only seems empty at first glance. Because even where there are no particles, quantum fields still exist, and they never behave absolutely quietly. Quantum fields do not maintain a constant value. Their value at any point in space is always slightly jittering. These jitters are called quantum fluctuations, and they are nothing other than consequences of Heisenberg's famous uncertainty principle. And at the quantum level, or even on larger scales if you are prepared to wait long enough. And by long, I mean very long, truly strange things happen from time to time, caused by unpredictable fluctuations capable of shifting some part of the system into a state of lower entropy, lower homogeneity. Therefore, even if we believe that the universe had a beginning and that it is not infinite in space, nevertheless, in an expanding universe, time and space become so vast that extremely, extremely improbable events can and will occur with 100% probability. It is improbable that a whole piano would spontaneously assemble in empty space. However, physicists Anthony Aguirre, Sean Carroll, and Matthew Johnson calculated that if you wait for a period of time a trillion times greater than the age of the universe, you will see it appear right before your eyes. The less probable an event, the longer you will have to wait. But if you have infinite space or infinite time, and especially if you have both, then any arbitrarily improbable events will occur an infinite number of times. The consequence we can derive from the hypothesis of the heat death of the universe is capable of horrifying, no, paralyzing anyone who seriously contemplates it. Yes, the thought that pierced Nietzsche, which I mentioned at the beginning. A few months after his epiphany, Nietzsche would write the book The Gay Science, where he very cautiously touches upon his idea at the very end, in the penultimate passage of the first edition of the book, which he would call The Greatest Weight. It reads as follows: "What if some day or night a demon were to steal after you into your loneliest loneliness and say to you, 'This life as you now live it and have lived it, you will have to live once more and innumerable times more, and there will be nothing new in it. But every pain and every joy and every thought and sigh and everything unutterably small or great in your life will have to return to you, all in the same succession and sequence, even this spider and this moonlight between the trees, and even this moment and I myself. The eternal hourglass of existence is turned upside down again and again, and you with it, speck of dust. Would you not throw yourself down and gnash your teeth and curse the demon who spoke thus? Or have you once experienced a tremendous moment when you would have answered him, 'You are a god, and never have I heard anything more divine'? If this thought gained possession of you, it would change you as you are, or perhaps crush you. The question in each and every thing, do you desire this once more and innumerable times more, would lie upon your actions as the greatest weight. Or how well disposed would you have to become to yourself and to life, to crave nothing more fervently than this ultimate eternal confirmation and seal. The last passage of this book was titled Incipit Tragoedia, the beginning of tragedy, and this same passage would become the preface to the main work of Nietzsche's life, Thus Spoke Zarathustra, a book for all and none. The central idea of Thus Spoke Zarathustra was intended to be eternal return. The concept of eternal return asserts that time repeats in an infinite cycle, and that the same events will continue to happen in exactly the same way, over and over again, for eternity. In formulating this concept, Nietzsche most likely proceeded from the following premises. If the universe has infinite time, and the amount of matter in it is fixed, then sooner or later any combinations of this matter will be exactly repeated. Even if Nietzsche was far from today's cosmological theories, his conclusion may turn out to be precisely correct. Because this very conclusion is physically possible based on the hypothesis of de Sitter equilibrium, proposed by cosmologist Andreas Albrecht. The main idea of this equilibrium version of de Sitter space is that the origin of our universe and everything that happens in it can be seen as the result of random fluctuations in an eternally expanding space containing only dark energy. At some point in this space, due to quantum processes, a jump to a very low entropy state occurs and a universe arises, which then gradually returns to its normal high entropy state, once again becoming a de Sitter universe. Just like that oxygen, were it to gather in one corner, would gradually redistribute itself evenly throughout the room, and everything repeats over and over in a circle for an entire eternity. Of course, no one says that in every specific Big Bang, the history of that universe will repeat the history of our universe one to one. But this is the horror of infinity. Given infinite time, sooner or later our exact universe will be repeated with any desired precision, and we will be here again, communicating with each other, and this will happen an infinite number of times. And furthermore, given infinite de Sitter space, Big Bangs evolving exactly into our universe occur at every moment an infinite number of times. This entire process is described by a model of the universe called eternal inflation. I apologize for digressing so much, but we all speak so dismissively and casually about eternity or infinity without truly pausing for a second to consider what actually lies behind these concepts. You might say, again, what does this have to do with us? No matter how many times the universe repeats, it will no longer be us. But here the question arises, what does it mean to be you? One often hears from people who consider themselves non-religious that life is one and that we live only once. But isn't there more religiosity in this assertion than in the opposite? In other words, these people are saying that their consciousness is fundamentally impossible to recreate. A strong statement, because if you break it down into its premises, it turns out that consciousness is something detached from the material world. How much time is needed for a new Big Bang? Well, there are some calculations suggesting that inflation will generate a new Big Bang in approximately 10 to the power of 10 to the power of 10 to the power of 56. It towards this years. And you know what? If an entire universe can arise from a vacuum due to quantum fluctuations, then an individual galaxy can do so with much greater probability, as it is less complex and requires less matter for its creation. And if we continue to follow this logic, then the emergence of a single solar system is more probable. Or no, a single planet, or even just today, this very moment, and all other moments of your life. But wait, in fact, the appearance of a separate thinking structure is even more probable. For example, a human brain that contains all your memories and imagines that it lives in a vast and complex world and is currently perceiving information, perhaps through a narrative exploring hypotheses that are likely unverifiable. You do not notice this illusion because for you, as an observer, there is no space and time beyond your consciousness. That is, you cannot be an observer of a dreamless sleep. You fall asleep and immediately wake up to a new day. If a suspicion has crept into your mind that this is some kind of schizophasia, then in fact, more than one generation of scientists has puzzled over similar ideas. The idea of the spontaneous appearance of a brain in the void is called a Boltzmann brain, and this concept gained new relevance around the year 2002, when some cosmologists began to worry that in many theories about the universe, a human brain arises much more often as a result of random fluctuations than the emergence of an entire universe in which evolution would then occur, resulting in the appearance of humans. Simply because the emergence of an individual brain from fluctuations is, I repeat, much, much more probable. If a new universe, as you recall, appears once every 10 to the power of 10 to the power of 10 to the power of 56 years, then a Boltzmann brain arises merely once every 10 to the power of 10 to the power of 50 years. This leads to the statistical likelihood that people are mistaken in their memories of the past, and are actually unfortunate Boltzmann brains, endlessly appearing in an empty universe and doomed to almost instantaneous destruction. And of course, we do not know all the variants of self-aware entities that are not forbidden by the laws of physics and which, accordingly, our universe is capable of generating. Boltzmann brains are child's play compared to what the universe is capable of generating in the model of eternal inflation. But I will not continue to provide examples, and I do not recommend that you do either. Even if you or I are not Boltzmann brains, such ideas still attract attention. Looking at the insane number of parameters that had to align for the human mind to appear, as discussed in the context of why Earth might seem to break the symmetry of the universe, one cannot help but wonder if infinite time or space is involved here. The idea of the possibility of fluctuation so strongly contradicts our notions of a rationally ordered cosmos that leading contemporary cosmologist Sean Carroll called it cognitively unstable. The point is not that it cannot be true, but that if it is, then in that case, we might as well abandon any attempts to understand the universe, because nothing makes sense. And Nietzsche is often called a nihilistic philosopher, supposedly denying life in his philosophy, but this is simply the most obtuse thing one could possibly say about Nietzsche's philosophy. If the doctrine of eternal return entails the meaninglessness of what happens, then the doctrine of the Overman, formulated in the same, "Thus spoke Zarathustra," should become a kind of demand addressed to the human will, so that such meaning might exist. The ruthless idea of eternal return excludes all hope for a heavenly life and any consolation. But Nietzsche believed that it is precisely the Overman who has the courage to say a loud and confident yes even to such a world, leaving behind all the illusory hopes with which religion, science, and philosophy have hitherto consoled. By the way, if you want to read some fiction about the Overman, then perhaps the closest I know would be Theodore Dreiser's Trilogy of Desire. At the end of the third book, eternal return is even mentioned. Unfortunately, Nietzsche himself was not an Overman and called himself a decadent. For Nietzsche, who had a tragic destiny filled with pain and suffering, the idea of eternal return was devastating, paralyzing, and absolutely terrible. In his notes, he wrote, "I do not want to start life anew. Where would I find the strength to endure it?" In creating the Overman and directing his gaze towards him, hearing him say yes to life, I, alas, myself, tried to say yes. Perhaps that is why Nietzsche refers to his deepest idea only in one passage from The Gay Science, in two passages from Thus Spoke Zarathustra, once in Ecce Homo, and once in The Will to Power, as if not daring to look this idea in the face for long. 8 years after the Epiphany and the most fruitful period of his life, Nietzsche went mad. There are different versions as to why this happened, including drugs for insomnia, heredity, schizophrenia, and so on, but there is no consensus on this issue yet. Some even genuinely believe that Nietzsche's madness had a psychogenic origin. Be that as it may, the illness did not leave the philosopher for a step, and on August 25, 1900, Nietzsche died in complete madness. And fortunately for him and for all non-Overmen, the heat death of the universe is only one of 5 possible versions described in the book The End of Everything by Catherine Mack, which largely informed this discussion, and not every scenario implies the hypothetical possibility of eternal return. Author Catherine Mack is a specialist in theoretical astrophysics, and her book is a fascinating read on these topics. Theoretical physicist Freeman Dyson, known to the general public for the Dyson sphere, in his article Time Without End, Physics and Biology in an Open Universe, Prokotinothitsis Mordeyork Tutuan sharply criticized the physics community for neglecting the topic of the end of the universe. Implying a lack of serious work on this subject, he wrote, "The study of the distant future today seems as questionable an occupation as the study of the distant past seemed 30 years ago. If the analysis of the distant future raises questions related to the ultimate meaning and purpose of life, let us explore them boldly and without embarrassment. However, based on what we have heard today, perhaps it is not worth doing so. But again, it is important to consider that much of what has been presented are reasoned hypotheses that may or may not be confirmed. These remain profound questions." This video explores sensitive topics about human physiology and gender dynamics from a scientific perspective, so it's not recommended for viewing with children or parents. Consider your reaction to the statement, "Humans evolved from apes." Are you amazed? Likely not. This lack of surprise is remarkable, like the idea that the universe originated from a point smaller than an atom, which once astonished but now feels mundane. The notion of human evolution from apes has become so familiar that it no longer shocks. But was there ever a moment when it truly stunned you? This concept, though scientifically grounded, clashes with our deep-seated views of ourselves, requiring some gritty details to spark genuine awe. Our species' name, Homo sapiens, wise man, is arrogant and unscientific, as science avoids vague terms like wise. I challenge you to view this discussion impartially, as an alien researcher might. A more fitting name, per modern scientific standards, would be naked ape, as humans are the only hairless species among 505 primate types. You may not realize how much of your behavior stems from animal instincts that have persisted for millions of years. Despite technological advances, Homo sapiens remains a naked ape, according to ethologist Desmond John Morris. His 1967 book, The Naked Ape, are sold over 20 million copies, becoming a landmark in anthropology. Compared to Stephen Hawking's A Brief History of Time, which hit 10 million, Morris's work profoundly shaped Western views, inspiring generations of biologists despite ongoing debates. The Naked Ape reveals stark truths about our bodies and psychology. You might think your actions are choices or culturally driven, but they're often rooted in instinct. Some of Morris's ideas amuse, others unsettle, and some provoke outrage. For instance, why do we have earlobes? These fleshy growths consume resources, are richly vascularized, and have many nerve endings, yet serve no clear function. Morris suggests they evolved as erogenous zones to enhance pair bonding, swelling during arousal to increase sensitivity. The book's core idea is that our loftiest traits, family, friendship, love, faith, are derivatives of ancient instincts. Ignoring this foundation risks trouble. Cultural progress meets resistance when it clashes with our biology, shaped when we were hunter-gatherer apes. A pivotal influence occurs in the womb, where the mother's heartbeat, heard by the fetus at 70 beats per minute, imprints comfort. Post-birth, 80% of mothers hold infants on the left side, near the heart, regardless of handedness, to provide familiar security. Rocking at 60-70 swings per minute mimics this rhythm, aiding sleep, a pattern we unconsciously replicate in stress through tapping or swaying. Mother apes maintain constant physical contact with their young, aided by infants' instinct to cling to fur. Human babies, however, lack the strength and fur to hold on as monkey infants do, yet they retain a gripping reflex. This reflex is observable in 6-month-old fetuses and newborns, who tightly grasp when their palms are stimulated, though they cannot sustain it like their primate cousins. Even more striking is the Moro reflex. When a baby is suddenly lowered, their arms spread, fingers open, and then close as if grasping to avoid falling. This reaction, persisting up to 8 weeks, is a vestige of primate instincts designed to ensure survival in treetop environments. Why are humans the only hairless apes? In the wild, naked skin seems impractical, vulnerable to scratches, bites, and environmental hazards. Unlike other mammals, except thick-skinned elephants, rhinos, or aquatic cetaceans, our lack of fur appears disadvantageous. Early theories suggested fur loss resulted from clothing or fire use, but these explanations are flawed, as such cultural developments occurred long after hairlessness evolved. Around 15 million years ago, climate shifts forced our ancestors from dense forests to open plains, where they competed with highly adapted animals like big cats and hyenas. Lacking the speed to chase down prey like predators, early humans developed a unique strategy: persistence hunting. They ran down prey until it collapsed from exhaustion, a feat impossible in thick fur which would cause overheating. Natural selection favored mutations that reduced body heat, leading to the loss of fur and the development of abundant sweat glands. Unlike other primates, humans have millions of sweat glands, enabling efficient cooling during prolonged activity. Bipedalism further minimized sun exposure by presenting only the head to direct sunlight, explaining why hair persists on the scalp. This adaptation made humans unmatched in endurance running, capable of outlasting faster prey like antelopes. Ultramarathoner Dean Karnazes, for example, ran 563 km in 80 hours without rest, showcasing this capability. Humans are also uniquely adapted for swimming. Unlike chimpanzees, who flounder in water, our streamlined bodies, with hair aligned to reduce water resistance, resemble those of aquatic mammals. Subcutaneous fat, more pronounced in humans than other primates, provides insulation in cold water, similar to seals. Wrinkled skin on fingers and toes, triggered by water exposure, is a neural adaptation that enhances grip, akin to grooves on Formula One tires. This trait likely aided our ancestors in hunting aquatic prey, such as fish or shellfish, in rivers and coastal areas. Hair loss in humans not only aided thermoregulation, but also enhanced the pleasure of physical intimacy, strengthening pair bonds. Unlike other primates, human lips are uniquely prominent and everted, serving as a sexual signal. Desmond Morris suggests that as our ancestors became bipedal, lips evolved to mimic the appearance of female genitalia, advertising fertility. Kissing, a near-universal behavior, allows partners to assess compatibility through taste and smell, with 59% of men and 66% of women reporting lost attraction after a first kiss. Morris posits that female breasts, unlike the flat chests of other primates, may have evolved to resemble buttocks, amplifying sexual signals as bipedalism shifted attention to the front of the body. Reduced body hair in females highlights these features, making them more prominent. Puberty accentuates sexual dimorphism. Women develop wider hips for childbirth, while men gain broader shoulders for physical strength. Apocrine glands, concentrated in armpits and genitals, activate post-puberty, producing odors retained by sparse hair. These scents, more abundant in women, may foster olfactory imprinting, where partners bond over genetically compatible smells. Flirting, often initiated by women through eye contact, is a universal human behavior. The white sclera of human eyes, unique among primates, enhances gaze detection, signaling interest. Smiling, rooted in infant expressions of loneliness and lowering eyes, a primate gesture of submission, convey friendliness, encouraging male approaches. Unlike most apes, where mating is rapid, human pair formation is slow and female-controlled due to the high investment in offspring. Monogamy, reinforced by sexual imprinting, romantic love, ensures partner fidelity, though infidelity remains common, with 50% of men and 30–40% of women engaging in extramarital affairs. The sexy son hypothesis suggests women may choose charismatic or dominant men to produce sons who will inherit these traits, spreading their genes. This explains attraction to bad boys, despite the risks. Evolution's blind trial and error process results in flaws, such as the shared airway for breathing and swallowing, which increases choking risks but persists due to developmental constraints. Human social structures and gender roles are deeply rooted in our evolutionary past, shaped by the demands of survival and reproduction. Desmond Morris, in The Naked Ape Kaish, argues that many behaviors we consider cultural are extensions of ancient instincts. Men's protective instincts, for instance, are evident in historical events like the Titanic disaster, where 75% of survivors were women due to the Women and Children First protocol. This behavior reflects a genetic drive to prioritize the survival of females, who are critical for species continuation due to their reproductive role. In early human societies, labor was divided along gender lines to optimize survival. Women, often pregnant or nursing, gathered carbohydrate-rich plants, which provided stable energy sources. Men, leveraging greater physical strength, hunted for protein-rich meat, a riskier but high-reward task. This division fostered male hunting groups, a social structure rare among primates, where maternal care typically dominates. Unlike chimpanzees, where females and offspring form the core social unit, human males bonded in cooperative hunting bands, sharing risks and rewards. These groups laid the foundation for male solidarity, seen today in team sports, military units, or even workplace camaraderie. Women's social strategies also evolved to mitigate risks. Morris suggests that women often maintained backup male relationships, platonic friends who could provide protection or resources if the primary partner failed, such as during a hunt. This behavior, while strategic, does not imply widespread dual mating. Genetic studies indicate that only 2–3% of children are non-paternal, suggesting infidelity was not a dominant strategy. Instead, women's social networks ensured stability, balancing dependence on male providers with community support. Pair bonding ceremonies, from weddings to public declarations, reinforce attachment and signal commitment to the group, reducing conflict over mates. Morris notes that men tend to fall in love faster, driven by visual cues and reproductive urgency, while women's attachment fades quicker if emotional or resource security wanes. This dynamic reflects the differing evolutionary pressures. Men maximize genetic spread, while women prioritize offspring survival. The hymen, a thin membrane in females, may have evolved to enforce sexual selectivity, signaling virginity and increasing male confidence in paternity. Its presence, valued in many cultures, aligns with male instincts to invest in their own offspring. However, its evolutionary origin remains debated, as it appears in only some mammals and varies widely among humans. Morris speculates it emerged to deter casual mating, raising the stakes for female partner choice, though cultural amplification has exaggerated its significance. Infanticide, though rare, reveals darker adaptive strategies. In resource-scarce environments, mothers may kill newborns to preserve energy for existing children or future reproduction. A study in Italy documented 110 cases of maternal infanticide, often linked to poverty or social stress. This behavior, seen in other mammals like lions, underscores the brutal logic of survival, where maternal investment is calculated to maximize long-term reproductive success. Women's limited reproductive window, roughly 400 ovulations compared to men's continuous sperm production, makes them the primary drivers of human evolution. Historically, only about half of men reproduced, while most women did, suggesting females exerted stronger selective pressure through mate choice. This dynamic explains why traits like male charisma or physical prowess persist, as women favored partners who could provide security or genetic advantages for offspring. Human behavior around territory, clothing, and food reveals our deep primate roots, shaped by millions of years of evolution. Desmond Morris, in The Naked Ape, argues that our homes, fashion, and diets are not merely cultural constructs, but extensions of ancient instincts adapted to modern contexts. These behaviors, often taken for granted, reflect our biological heritage as both primates and predators. Humans, like other primates, are territorial animals, a trait that governs how we organize our living spaces. Our homes mirrored the defended territories of our ancestors, whether they were treetop nests or savanna camps. Morris suggests that the modern house or apartment is a direct descendant of these primal territories, complete with symbolic markers like fences, gates, or nameplates that signal ownership. Inside, spaces are divided into functional zones: kitchens for feeding, bedrooms for mating and sleeping, mimicking the structured nests of apes. This territorial instinct drives behaviors like decorating, which personalizes space, or disputes over property lines, which echo primate conflicts over feeding grounds. Unlike solitary predators like tigers, humans live in cooperative groups, balancing individual territory with communal spaces. A city apartment block, for instance, houses hundreds of family units, each with its own nest, yet sharing common areas like hallways or courtyards. This arrangement reflects our hybrid nature. We crave the security of a personal domain, but rely on group cooperation for survival. Morris notes that territorial disputes, from neighborly feuds to international wars, stem from this instinct, amplified by our ability to create abstract boundaries like borders. Clothing, a hallmark of human culture, originated not for warmth, but for social signaling. Morris posits that early humans, having lost their fur, used clothing to conceal sexual signals, such as genitalia, to reduce constant mating conflicts in close-knit groups. Over time, clothing evolved to protect against environmental hazards like cold or sun, but its primary role remained social. In colder climates, layers of animal hides or woven fabrics became essential, yet even here, decoration, beads, dyes, or patterns serve to advertise status or group identity, much like the colorful fur of other primates. Paradoxically, clothing can also enhance sexual signals. Modern fashion, from high heels to tight jeans, exaggerates traits associated with youth or fertility. High heels, for example, elongate the legs and tilt the pelvis, mimicking the posture of younger females, while makeup amplifies facial signals like flushed cheeks or full lips. Morris points out that cultural norms often suppress natural signals, body odor, or exposed skin, yet we subvert these rules through perfumes or revealing styles, betraying our instincts. An intriguing evolutionary relic is paradoxical undressing in hypothermia, where victims strip naked as vasodilation creates a false sense of warmth, exposing our vulnerability to primal responses. Human diets reflect our dual identity as omnivorous primates and opportunistic predators. Unlike strict carnivores like lions or fruit-focused primates like gorillas, humans combine both tendencies. Morris highlights that we eat large, hot meals like predators, preferring cooked meat for its concentrated protein, yet crave sweets like primates, drawn to the quick energy of fruits or honey. This hybrid diet shaped our social behaviors. Communal meals, from family dinners to feasts, strengthen group bonds, much like grooming does for apes. Our predatory side manifests in hunting and cooking, which require planning and cooperation, traits that distinguish us from other primates. Chimpanzees may hunt small prey, but they lack the systematic approach of human hunter-gatherers, who tracked large game and shared kills. Cooking, a uniquely human innovation, not only made food safer and tastier, but also fostered social rituals as groups gathered around fires. Meanwhile, our primate heritage drives our love for carbohydrates, grains, roots, or sugary snacks, evident in the global obsession with desserts or soda. Food preferences also reveal evolutionary compromises. Sweaty palms, a stress response, likely evolved to improve grip during hunts, aiding spear throwing or climbing. Our taste for salt, essential for electrolyte balance, can lead to overconsumption in modern diets, contributing to health issues like hypertension. Morris emphasizes that these instincts, while adaptive in ancestral environments, often clash with today's abundance, highlighting the tension between our biology and culture. Territoriality, clothing, and food habits underscore our struggle to reconcile ancient instincts with modern life. Urban sprawl challenges our need for defined territories, leading to stress in crowded cities. Fashion, while creative, often exploits sexual instincts, driving consumerism. Our diets, shaped by scarcity-driven instincts, face an environment of excess, contributing to obesity and related diseases. Morris argues that recognizing these roots can help us navigate these conflicts, aligning our behaviors with our biological heritage for a more balanced existence. Human aggression and the drive for competitive sports are not mere cultural phenomena, but manifestations of deep-seated evolutionary instincts. In The Naked Ape, Desmond Morris argues that our capacity for violence and our love for games like football or boxing stem from the same biological impulses that shaped our ancestors' survival strategies. These behaviors, often viewed as modern or societal, reveal our dual nature as cooperative primates and opportunistic predators. Aggression in humans is a complex trait, rooted in our primate ancestry but amplified by our predatory adaptations. Like chimpanzees who engage in territorial skirmishes or dominance displays, humans are wired for conflict to secure resources, mates, or status. However, unlike most primates, our ancestors evolved as hunters, pursuing large game in coordinated groups. This predatory lifestyle required not only cooperation, but also controlled aggression, directed at prey or rival groups. Morris suggests that this dual role, cooperative ally and aggressive hunter, created a unique tension in our psychology. In early human societies, aggression was tempered by social bonds. Face-to-face combat, like wrestling or fistfights, allowed for displays of strength without lethal outcomes, as opponents could signal submission to end conflicts. These interactions mirrored primate dominance rituals, where baring teeth or posturing resolved disputes without bloodshed. However, the invention of projectile weapons, spears, bows, and later guns, disrupted this balance. Unlike physical combat, ranged weapons bypass natural limiters, enabling mass killing from a distance. Morris notes that this technological leap, combined with our tribal instincts, has fueled devastating wars, a trait shared with chimpanzees, who also engage in lethal group conflicts. Our physiological responses betray this aggressive heritage. Sweaty palms during stress, often seen as a sign of nervousness, likely evolved to enhance grip during hunts or fights, improving weapon handling or climbing. Similarly, the adrenaline surge in confrontations prepares the body for fight or flight, a mechanism honed over millions of years. Yet in modern contexts, these responses can misfire, leading to chronic stress or impulsive violence when social triggers mimic ancestral threats. Sports, particularly competitive ones, are a direct outlet for our predatory and aggressive instincts. Morris argues that games like football, rugby, or hunting simulations, e.g. archery, mimic the dynamics of ancestral hunts. In football, for instance, players chase a prey, the ball, coordinate as a pack to outmaneuver opponents, and defend territory, the goal. The crowd's roars echo the communal excitement of a successful hunt, reinforcing group cohesion. Even non-contact sports, like running or swimming, tap into our endurance-based hunting strategies, where persistence outlasted faster prey. This connection is not merely metaphorical. The physicality of sports, tackling, sprinting, or throwing, engages the same muscle groups and neural pathways used by our ancestors to stalk and kill. Morris points out that spectators, too, are drawn in by instinct. Cheering for a team mirrors the tribal loyalty of hunting bands, while booing rivals reflects territorial defense. The global obsession with sports, from the Olympics to local leagues, underscores their role as a socially acceptable channel for aggression, reducing the need for actual violence. However, sports can also amplify destructive tendencies. Hooliganism, where fans clash violently, reveals how thin the veneer of civility can be when tribal instincts are aroused. Morris suggests that while sports sublimate our predatory drives, they also risk reigniting the same group rivalries that fuel wars. The challenge lies in harnessing these instincts constructively, using competition to foster unity rather than division. In modern societies, aggression and sports intersect with technology and culture in complex ways. Media glorifies violence in films or video games, offering virtual outlets for predatory instincts but potentially desensitizing us to real harm. Urban environments, with their anonymity and crowding, can trigger territorial aggression, from road rage to gang conflicts. Meanwhile, organized sports, while beneficial, often fuel hyper-competitive cultures that prioritize winning over cooperation, echoing the dominance hierarchies of our primate ancestors. Morris argues that understanding these instincts is crucial for managing their darker sides. By channeling aggression into structured activities like sports, societies can reduce violence, but only if they address the underlying tribalism that fuels division. Education and awareness of our biological roots can help us temper impulsive reactions, fostering cooperation over conflict. For instance, international sports events, when inclusive, can unite disparate groups, turning rivalries into shared celebrations of human potential. Our aggressive and competitive drives, while potentially destructive, are also sources of creativity and resilience. The same instincts that drove our ancestors to hunt megafauna or defend territories enabled us to build civilizations and explore the stars. Morris emphasizes that by acknowledging our naked ape nature, we can redirect these energies toward constructive goals, balancing our primal urges with our capacity for reason. War, one of humanity's most destructive behaviors, is not a modern invention, but an extension of ancient instincts rooted in our primate and predatory ancestry. In The Naked Ape, Desmond Morris argues that warfare emerges from the same tribal instincts that once ensured group survival, now amplified by technology and abstract ideologies. By exploring the evolutionary underpinnings of war and tribalism, we can better understand their persistence and seek ways to mitigate their devastating consequences. Humans are inherently tribal, a trait inherited from our primate ancestors, who lived in tight-knit groups to survive predators, secure food, and raise offspring. Chimpanzees, our closest relatives, exhibit similar tribal behaviors, forming bands that defend territories and occasionally raid neighboring groups, sometimes with lethal outcomes. Morris suggests that human tribalism evolved to enhance group cohesion, fostering loyalty and cooperation among members. In early hunter-gatherer societies, tribes of 150 individuals shared resources, hunted together, and protected each other, creating a sense of us versus them. This us versus them mentality, while adaptive in small-scale societies, becomes problematic in larger, interconnected populations. Morris notes that our brains are wired to recognize group markers, physical traits, languages, or customs, and to distrust outsiders. This instinct, once crucial for identifying allies in a dangerous world, now fuels prejudice, xenophobia, and nationalism. The same loyalty that binds families or teams can escalate into hostility when group identities clash, whether over land, resources, or ideologies. Tribalism also shapes social hierarchies. Like other primates, humans establish dominant structures to maintain order, with leaders emerging through strength, charisma, or resource control. In early tribes, alpha males or females coordinated group efforts, but modern societies replace physical dominance with symbolic power, wealth, titles, or political influence. These hierarchies, while stabilizing, can exacerbate tribal conflicts when leaders rally followers against perceived threats, real or imagined. War is tribalism on a catastrophic scale, enabled by our predatory adaptations and technological advancements. Unlike most animals, whose conflicts are limited to displays or small-scale skirmishes, humans combine primate territoriality with the strategic aggression of hunters. Morris explains that our ancestors' hunting skills, coordination, planning, and tool use were repurposed for warfare as tribes competed for scarce resources. The invention of projectile weapons, from spears to missiles, removed the physical and emotional barriers of close combat, allowing mass killing without the natural checks of submission signals. Historical and modern wars reflect this lethal blend of instincts and technology. Morris draws parallels with chimpanzee raids, where males silently infiltrate rival territories to kill or drive out competitors. Human warfare, however, scales this behavior to millions, with ideologies like religion or nationalism justifying violence as a defense of the tribe. The 20th century alone saw over 100 million war-related deaths, a testament to our capacity for self-destruction. Unlike chimpanzees, whose conflicts are limited by physical proximity, humans wage war across continents, using tools that amplify our aggression far beyond its evolutionary purpose. Physiological responses underpin this behavior. During conflict, adrenaline and cortisol prepare the body for action, sharpening focus and strength. Morris notes that sweaty palms, a stress response, likely evolved to improve grip during hunts or fights, aiding weapon use. These reactions, adaptive in ancestral environments, persist in modern warfare, where soldiers face psychological strain from prolonged alertness, contributing to conditions like PTSD. In today's world, tribalism and war manifest in both overt and subtle ways. Global conflicts, from territorial disputes to ideological wars, reflect our inability to transcend group loyalties. Even in peacetime, tribal instincts fuel division. Political polarization, cultural clashes, or sports rivalries that erupt into violence. Social media amplifies these tendencies, creating echo chambers where group identities are reinforced and outsiders are demonized. Technology exacerbates the problem. Nuclear arsenals, drones, and cyber warfare make conflicts deadlier and more impersonal, bypassing the face-to-face interactions that once limited violence. Morris warns that our tribal instincts, untempered by reason, risk catastrophic consequences in an interconnected world. Yet these same instincts can be redirected. International cooperation, such as global health initiatives or environmental agreements, harnesses our group-oriented nature for collective good, turning us into a planetary tribe. To mitigate war's destructiveness, Morris advocates recognizing our biological roots. Education about our shared humanity can weaken us versus them barriers, while diplomacy and conflict resolution can channel aggression into negotiation. Sports, arts, or collaborative projects offer outlets for tribal energy, fostering unity without bloodshed. By understanding that our drive for war stems from instincts that once ensured survival, we can consciously choose paths that prioritize cooperation over destruction. War and tribalism, while deeply ingrained, are not inevitable. Our capacity for reason, unique among animals, allows us to reflect on our instincts and adapt. Morris emphasizes that acknowledging our naked ape nature is the first step toward mastering it. By redirecting tribal loyalty toward global challenges like climate change or pandemics, humanity can transform its aggressive potential into a force for survival and progress. The same instincts that drive us to divide can, with effort, unite us in pursuit of a shared future. Religion, a cornerstone of human culture, unites billions across diverse societies, yet its origins lie not in divine revelation but in the primal instincts of our primate ancestors. In The Naked Ape, Desmond Morris argues that religious behaviors, rituals, beliefs, and devotion stem from the same evolutionary drives that govern group cohesion and submission to dominant figures. By examining religion through an ethological lens, we uncover its roots in our biology and its role in shaping human societies. Humans, like other social primates, thrive in hierarchical groups where order is maintained through deference to leaders. Chimpanzees and baboons submit to alpha individuals through gestures like bowing, grooming, or averting gaze, ensuring group stability and reducing conflict. Morris suggests that human religion evolved as an extension of this instinct, redirecting submission from visible leaders to abstract supernatural entities, gods, spirits, or cosmic forces. This shift allowed early humans to unify larger groups beyond the physical presence of a single dominant figure, fostering cooperation across tribes. Religious rituals mirror primate submission behaviors. Kneeling, bowing, or prostrating during prayer parallels the lowered posture of a subordinate ape before